Good morning. Good morning, everyone. Good morning. If I could have your attention, please. All right. Yeah, we're about to kick off day 2. As a matter of fact, yeah, perfect. We're going to kick off day 2 now, Tuesday. So we're here. So we managed to get through Monday. Did you have a great time? Nice. And I hope you managed to, I don't know, find a good dinner spot or something. So a couple of notes about today. So we're going to have talks as usual. Exhibit hall, same as usual. There's an RFNOC tutorial. I don't know if you have to sign up for that, or I'm not quite sure. As well as the introduction to GNU Radio with Python. Those are in the workshop rooms. Capture the flag, of course, going on. We're going to display the scores again at the end of the day. I have not quite sure what this means, but I'm guessing this might be a fox hunt going on or something today. So, which is good for you guys because you can actually beat Danny, maybe, possibly, because he can't come here and find the devices. So, but he's pretty smart, so I wouldn't bet money on that. Anyway, now today's a little bit different because we have breakout sessions. So we're gonna do talks until like 3-ish, and then we have breakout sessions, and they are still part of the conference. So sure, if you really want to sort of step out of the venue at that time, you can do that. But we are really, really hoping that you would, join us and talk about various topics that are related to GNU Radio. So I won't read them out all individually. You can just come and join. The actual schedule has the location, and the only breakout room I just want to mention is the last one, Women at GRCon. It's led by Sam, and she just wanted to make sure that we don't make it, sell it as exclusive. So it is. So the topic is Women at GRCon, but that doesn't mean others are not welcome there. Let's see. Okay, all right. So we're gonna start at 9. I just few more points. Lightning talks, same as yesterday. We still have slots available, and you don't need slides or anything. All you need is like 5 minutes of content, and it has to be vaguely related to this conference, please. But yeah, we are interested in. I mean, you could just come up and say, "I have this great idea. I want to build, an application that does blah blah blah. Does someone want to join me? I have these ideas." That would be a perfect lightning talk. You do not have to overthink this. Of course, if you have like something you want to demo real quick, that also works. We can accommodate you as long as it fits in 5 minutes or less. Quick reminder, join us on chat. It's really, really active. And it's a great place to throw questions around. Yesterday I was able to throw in a question in chat where I wasn't able to ask it in person because I had like something else going on. Really, really convenient. And of course, we hope that you hang around there all year round. Wi-Fi, quick reminder of the the password, #GNU 2022. And we still, amateur radio exams on Thursday. I mentioned this yesterday. You can still sign up. I think you can sign up pretty last minute, but you have to sign up. And then you'll be licensed. And then next year we can. Walk-ins are welcome. Okay, I'm sorry. It just helps us if you sign up. Okay, it helps us if you sign up. If you want to try last minute, like all of you are smart enough to pass technician, probably. I mean, come on. You guys are smart. You can take credit for that. I mean, you came to this conference after all. All right. Now there's a team forming around the CTF. So you can just stop. So if you say, I want to join the CTF, but I don't really want to do it by myself, you are not alone. Other people are in the same situation and have decided to open a team. I think this is one of the organizers. So you can go to the registration desk for information, and then you can join a CTF team. All right, so 2 minutes before we start the program, I have a quick announcement on the schedule that did not make it into the slides. So we had a little bit of a hiccup, nothing major. We just have to shuffle some of the talks around, which means the opening talk. So I mean, we are in DC, right? So the president, of the GNU Radio project was gonna give an opening talk, but we didn't quite get But he can't be here, so we had to upload a video. We didn't quite get that on time. So Steve Croft from SETI is gonna he's gonna do the first talk. Then there'll be the NI sponsored talk. And then we'll have the keynote as planned. Keynote is going to stay where it is. But then instead of Steve and my talk, which would have been after the keynote, we'll then have the project update from Derek. So with that, I'm going to hand it off to our session host of today, who's Aaron, and our first speaker, Steve. Welcome, everyone, to Tuesday of GRCon.
Thanks. So how do I switch over to this one? Okay, great. Yeah, thanks. So I'm going to talk a little bit about SETI, the search for extraterrestrial intelligence, but more broadly, I want to talk about the SETI Institute. So I'm actually wearing two hats here today. One is my SETI Institute hat, and one is my Berkeley SETI Research Center hat, but we're really all sort of one big happy family in the SETI community. So I'll give you a little bit of background about what the SETI Institute does, talk a little bit about the work that I do specifically, and then I'm happy to take questions and to refer questions out to some of my other colleagues that are here this morning. SETI, the search for extraterrestrial intelligence, began in its modern form at the Green Bank Observatory in 1959 with this Project Ozma search that was done by Frank Drake, who was, I think, 29 years old at the time. Frank sadly just passed away earlier this year, but he was really one of the pioneers in the field, also somebody who was very much involved with the SETI Institute from its foundation. And also around the same time, NASA and the National Science Foundation I guess the National Academy of Sciences, were beginning to consider the possibility of life beyond Earth. And this was back in the day when we really didn't know very much about the possibilities for life in our solar system or outside our own solar system. There's a lot more data that we have now that's really driving the modern search for life beyond Earth. So as I say, Frank, Project Ozma took place at the Green Bank Observatory, and Frank really had a long and illustrious career. There's a lot of memorials if you want to go online and look in the media since he passed away a week or two ago. Really, really incredible guy who was a mentor to the younger generation as well, and he really will be missed. So another thing that happened in the early 1960s, again at the Green Bank Observatory, was Frank put together what's now known as the Drake equation, which really was an attempt to parameterize what we know about the possibilities for life beyond Earth. So there's this number n on the left, Drake's n, the number of technological civilizations that exist, in this case in our own galaxy. And Frank multiplied these numbers together on the right, so there's the rate of formation of stars in the galaxy, there's the fraction of those stars that have planets, the number of habitable worlds, so sort of could be Earth-like planets per system that has planets, the fraction of those on which life arises, the fraction of planets with life on which intelligence arises, the fraction of planets with intelligence that develop technology, communications technology specifically, which obviously is the interest in the room here today, and the duration that technology persists for. And so we've had radio technology for about 100 years. You could put the L equals 100 on the right. And then all of those other numbers, so R star is sort of order 1, FP, we now know, we didn't know back in the 1960s, but we now know that pretty much every star has planets. And probably the number of sort of habitable worlds per system is around 1. So there's these, there's these three numbers, I guess, right? But this is sort of saying what I just said. Every star in the sky has one or more planets. Many of them are Earth size. About 20% of them are rocky, habitable zone worlds, so the right distance from their star where liquid water could exist on the surface. And so there's maybe 10 to 60 billion, depending on the numbers, the exact numbers, Earth-like planets in this habitable zone where liquid water could exist on the surface in our galaxy alone, and that's not even accounting for other galaxies. So there's a lot of real estate out there, and the question is, does life arise where you have the conditions and the ingredients? So I mentioned this already. We know these three numbers on that are with check marks on the left here, and then we really don't know these other numbers here. Are we going to have technology that persists, that's detectable for a long period of time? And what are the chances that life and intelligence and communication arises on planets where the conditions are suitable? So this is really what we're trying to find out. And in particular, in the context of the SETI Institute, it's not just a focus on the communicating technology, it's a focus on the habitability and the fraction of planets where life arises, and really sort of synthesizing all of these fields in modern astronomy and astrophysics that enables us to address these questions. So just to sort of put things on the map here. So I'm based at UC Berkeley at the Berkeley SETI Research Center. I also have, again, another hat that I wear, which is my affiliation with the SETI Institute. There's a few of us at Berkeley SETI who also have SETI Institute affiliations. And then some of you are familiar, I know, with the Allen Telescope Array, which is the 42-element antenna array. These are 6-meter antennas that are based up at the Hat Creek Radio Observatory, about a 4-hour drive north of the San Francisco Bay Area. And I know several of you in this room have been out to Hat Creek and out to the ATA for a hackathon that we had there. We're hoping to do that again, perhaps in 2023. And I know there's been a lot of interest at this meeting as we're sort of coming out of the sort of acute phase of the pandemic. I hope we'll be able to get folks together again up there and really get hands-on. It's a really fun place to go, and sort of fun to be able to roll up your sleeves and actually plug stuff into a radio telescope, which we're going to have a keynote from Tony Beasley from the National Radio Astronomy Observatory tomorrow. And the barrier to sort of playing around with Tony's telescopes is a little higher than it is to playing around with ours. We're a little bit more kind of roll up your sleeves and plug stuff in, and we actually have some USRPs that are plugged into the back of the telescope there that you can play around with. So again, just to sort of make the distinction with Berkeley SETI and Breakthrough Listen, the other hat that I wear, so I'm the project scientist for Breakthrough Listen on the Green Bank telescope. This is at the Green Bank Observatory where Frank's experiments started in the 1960s. But the Green Bank telescope is a really huge single dish. It's a 100-meter single dish. It's about 7,000 tons of moving parts. If you get the chance to go out to Green Bank, West Virginia and check it out, it's really cool. You know, again, this is sort of a telescope that is it's scheduled sort of pretty I don't want to say aggressively, but you know, there's not a lot of it's hard to get time on the Green Bank telescope. It's hard to sort of play around with the Green Bank telescope, and so a lot of the sort of prototyping work and a lot of the kind of pioneering work that we're doing in driving the technology forward, that technology development is taking place up at the ATA. I keep on saying I wear a lot of hats. The other hat that I wear is I run our undergraduate research program, and actually Shane Smith here, who's in the audience now at Aerospace, is a graduate of our research experience for undergraduates program. So if you want the real kind of you know, honest opinion from Shane, then go and catch him at the coffee break, and you know, do refer your undergrads to us as well. I think we have a fun time with them for a 10-week paid summer research internship. The SETI Institute also runs an REU program. So again, our focus is more on sort of the radio search for extraterrestrial intelligence, a little bit of optical searches. The SETI Institute's REU is broader, sort of covering life in the universe and all the other work that goes on at the SETI Institute as well. So I mentioned the Allen Telescope Array. This is wholly run and operated by SETI, and you know, again, 42 6-meter dishes. And the SETI Institute, you know, as I already said, basically is leading, this is sort of the mission statement, humanity's quest to understand the origins and prevalence of life and intelligence in the universe, and also to share this knowledge to inspire present and future generations. And maybe, Rebecca, if you just raise your hand in the back there. So Rebecca McDonald, who's the communications lead at the SETI Institute, is here as well, and we'll be happy to talk to you about that and about you know, the other sort of, some of the other things that I'm going to talk about today. So this really sort of comes under this umbrella of this question, are we alone? And, you know, as I mentioned, this is something that the national academies were looking at even as early as the late 1950s. There was a little sort of blip in the 80s and 90s, actually more of kind of a big blip, when people in Congress decided that this sort of little green men hunt was an easy target to have its funding cut. And it's taken a while to sort of rebuild the credibility of the field. And again, the fact that we now know that there are planets everywhere in our own galaxy has, I think, kind of made this seem a little bit more like a proper scientific field that's open for investigation, as opposed to sort of the tinfoil hat brigade kind of, you know, waving a coat hanger around somewhere in the middle of a field. So we now have the tools and the technology to find out. And again, you know, NASA has Mini Cooper-sized robots driving around on Mars. I'm sure you've all seen the images from the James Webb Space Telescope, which is one of its primary missions is to look for signs of biology, so-called biosignatures in the atmospheres of planets around other stars. And then by extension from biosignatures, you know, there's also been a little bit of rebranding in the SETI field to term this technosignature searches. So biosignatures looking for biology, technosignatures looking for technology. And I'm sure I don't have to tell folks in this room that, you know, the Earth is detectable the Earth's technology is detectable. Actually, the Earth outshines the sun at some radio wavelengths, in narrow bands. So if you're looking with a large antenna from a large distance away, then it would be pretty obvious that that the Earth was inhabited by a technological civilization. Another interesting point, there's a great paper that came out recently by one of our colleagues at Penn State, Jason Wright. And Jason makes the point that, if you were an alien visiting the solar system, you'd find there's only one world that we're aware of that has biology, but there's actually several worlds that have technology, and it's the technology that we've sent out there, our space probes. We've got, the rovers that are driving around on Mars. So you'd actually see signs of technology on more than one planet in our own solar system. And if you sort of factor that back into the Drake equation and you factor the longevity of that technology, maybe the technology isn't still operating, but the Apollo sites on the moon are going to be around for a long while, maybe even after a lot of evidence that's here on Earth has been sort of erased by the weather and plate tectonics and all this kind of stuff. So it's not clear that that biosignatures are necessarily the winning horse in this race. If you want to sort of bet on one or the other, then I think the jury's still out as to which is the best way forward. And again, I do want to emphasize the SETI Institute, is doing sort of aspects of all of the above, not just the search for extraterrestrial intelligence. So the SETI Institute is organized under these sort of three primary missions: the research mission to explore, the education mission to inspire, and then a broader kind of outreach program to engage. And there's a lot of great outreach that's going on. There's, I think that's that's in a later slide. I'll come back to that. But just to give you some sort of facts and figures about the SETI Institute, many of you are familiar, I'm sure, at least, Jill Tarter probably rings a bell. Jill Tarter and Tom Pearson founded the SETI Institute sort of out of a kind of Silicon Valley mindset, really, in the NASA Ames Research Center in 1984. There's now, I'm not sure whether this is quite up to date, but there's over 90 PhD research scientists and around 50 research affiliates, 10 professional staff in education, communications, and outreach. And again, Rebecca can tell you a lot about that. They've supported this meeting as well, providing, I think you've all got the logo on your badge that was designed by the designers at the SETI Institute. So, there's some real good resources that we can tap into as the GNU radio community here as well. $25 million annual operating budget. And a lot of that comes from federal grants and contracts. And I'll mention again briefly later that if you're interested in becoming a principal investigator with the SETI Institute, again, Rebecca can give you information about how to do that. SETI Institute's the prime contractor to NASA for planetary protection. Mentioned they manage and operate the ATA, administer and manage education programs in partnership with NASA and the National Science Foundation, formal and informal curriculum materials for education programs, and a real active program in public outreach to share our science with the general public. So here's some of the leading figures at the SETI Institute. So I mentioned Rebecca already, Andrew Simeon, who's also my boss at Berkeley, again, sort of somebody who wears two hats as the director of the SETI research program at the SETI Institute. And, again, some other folks that you might have seen here, particularly Seth Shostak, who's very active in the education program. So all these folks are available, to support and help manage grants and other programs. And again, we'd really encourage you. There's been some talk about the sort of organizational aspects of this, which I won't really touch on now. But GNU Radio is now, under the umbrella of the SETI Institute. And so, you here in this room have access to these resources to help support your work. A lot of funding sources. Again, a lot of it is, as I say, through contracts and grants. This is just a sampling of the folks that have funded the work going on at the SETI Institute. Again, sort of a way to break this down, really, in terms of this question, are we alone in the universe, is to take this into these three domains: the structure of the universe, planets and habitability, life, complexity, and intelligence, and then breaking this down into 6 disciplines that we use to address this: astrophysics, exoplanets, planetary exploration, astrobiology, climate and geoscience, and then the search, again, for technosignatures, which is sort of my area of expertise. So SETI Institute supports research across the natural sciences, again, not just SETI, NASA science mission support, field expeditions, lab research, ground-based astronomy observations in radio and optical, space-based operation observations, Hubble, Kepler tests, some of these NASA missions, technology and instrumentation development, advanced data analytics, and data management. And we explore to understand stellar and planetary evolution, planetary environments and habitability, the nature and origins of life, and the evolution of intelligence and technology. And I mean, these are really sort of pretty broad topics. And again, this technology, the technosignature work in particular, the work going on at the Allen Telescope Array, I think is sort of what's most relevant for the folks in this room. And it really is kind of hands-on, DSP, plugging stuff into antennas, anomaly detection, time series, data streams, high performance computing. There's a lot of stuff where I think we can kind of work together and do good stuff. So a day at the office can involve some pretty varied topics and some pretty varied different subjects that this breaks down into, and the interrelationship between all of those subjects as well. So I mentioned the work going on at the Allen Telescope Array, and particularly the hackathon. That again, some of you in this room will recognize yourselves in this photo. You can go and read the sort of the report from this meeting that we had up there. For those of you that have been up to the ATA, I will say, if you're going to come up to the ATA, then there's going to be a sort of rat's nest of cables, because there's no Wi-Fi up there, because you don't want to interfere with the observations. So you've got to plug in over Ethernet into some big switches. But from those of you who remember the signal processing room at the ATA, which was also a rat's nest at the time that you came up there, the new director who moved in, Alex Pollack, has really kind of reorganized that. And I think not just in terms of the how nice it looks in there now and how well organized it looks, but also in terms of the performance of the antennas and the work that's going on. And I'm not sure whether is Wael in the audience here. Let's see Wael. Oh yeah, oh, great. Okay, so we got some of the crew from the ATA here. Wael Farrar, who is one of the scientists up here. Luigi Cruz, who I think many of you know sort of from his work in GNU Radio, but has also been working up there, and Sebastian Obenberger, who are all there at the back. And if you want to go chat with them about the ATA and sort of ways to get involved there as well, I'm sure they'd be happy to chat with you about that. So GNU Radio at the ATA, again, has sort of come on in leaps and bounds. Really, I think sort of initiated at that hackathon that we had, but there's been folks working on that, including some undergraduate students who've actively been developing the program. I'd be remiss as well if I didn't mention Daniel Esteves, who's been doing really amazing work with the ATA. Check out his blog and some of the work that he's been doing for an idea of the capabilities that the ATA has and that the GNU Radio backend at the ATA has. It really, it's a sea change from what it was a few years back. I mentioned our undergraduate programs, so both the Berkeley and SETI Institute undergraduate research programs take the students up to the ATA. They get some hands-on training, again, led by Danny Esteves and by Derek Kozel in the use of GNU Radio more generally, and then they get to sort of transfer that hands-on to actually plugging into the back of the telescope and doing some radio telescope observations. So I think this is really a great program, and again, we'd welcome more involvement with that. Danny has some materials that he developed for the REU program. There's also some videos, which I've been remiss in getting uploaded, but we have some tutorial videos from this summer that I'm going to put up on YouTube, if you want to check those out for yourself or for students working with you. Just a few sort of screen grabs here. Detecting Voyager One at the ATA. I always love detecting Voyager One, firstly because it's 20 billion kilometers away and it's got a 20-watt transmitter, we can pick that up, which I think is really neat. And secondly, this is a sort of stand-in for a real technosignature, right? It's in the outer solar system. I mean, we still got to go, maybe 100,000 times further away to reach the nearest stars, so the power requirements go up, a fair bit. But it gives us this demonstration that this is possible, that these detections of these signals from vast distances are possible with the equipment that we have, which I think is really cool. I mentioned already, SETI Institute and GNU Radio have joined forces. So SETI Institute handles the contracts and grants and all of this sort of support for the GNU Radio project. And again, this is available to you, in this room if you have ideas for proposals that you want to put in. We've also used GNU Radio at outreach events that we've done, again, sort of both with the SETI Institute and with Berkeley SETI. Some good stuff that DeepSig helped us out with at a couple of exhibits, and people sort of seeing these sort of hands-on DSP applications and realizing that these can be applied to the search for life, I think is a powerful message that we can get across the public. So again, Tony Beasley is going to talk tomorrow, I think, mostly about satellite constellations and radio astronomy. But for those of you who've seen the movie Contact, the the Jodie Foster character here, I think, inspired at least in part by Jill Tarter at the SETI Institute. We're still not sort of really plugging in the headphones to the array and kind of listening for stuff. I think sort of the Breakthrough Listen project has maybe not helped very much as well with the idea that we're not actually listening. Of course, we're doing digital signal processing and detection and anomaly detection. But there is actually now going to be a project for the first time that is going to do SETI on the VLA, and this is driven out of the SETI Institute in collaboration with the National Radio Astronomy Observatory. Rather contrived acronym, the Commensal Open Source Multimode Interferometer Cluster Search for Extraterrestrial Intelligence, or COSMIC. And again, this is the first use of the VLA for SETI. I mentioned earlier, Tony's probably not going to give you large amounts of time on the VLA to do your science, but the power of this instrument that's being developed at the SETI Institute is that it's going to do commensal observations, essentially. So commensal is sort of eating at the same table, basically. So you've got a primary user who's pointing the telescope, maybe looking at the pulsar and the green beam in the center, and then you can simultaneously do beamforming that phases up on other targets in the field that are of interest for the SETI searches, and we can do that processing completely independently without interfering with the primary user. And again, this is really a win-win. Mentioned the outreach stuff, so Seth's radio show, the Big Picture Science, SETI talks, lectures, a lot of these are streamed live. There's also some Facebook Live stuff. There's been some great work with artists in residence at the SETI Institute. If you are or if you know of artists that will be interested in taking part in that, again, Rebecca can fill you in on the details. Education, so the Sophia telescope 747 with a big hole cut in the side, that mission is winding down now, but the SETI Institute has been instrumental in training high school science teachers, actually flying them up on the Sophia mission, and also leading this space science program for Girl Scouts in partnership with the University of Arizona and the Astronomical Society of the Pacific. So, a few statistics about how many interns have been reached, how many teachers have been reached, and then, again, these sort of broader partnerships that are really, I think, having an impact. You may have come across FDL at some point. So this is a public-private partnership focused on AI and machine learning, and its overlap with space science. Again, this doesn't have to be SETI. I'm wearing my sort of, technosignature search hat here, but there's a lot of programs that go on sort of across the sciences where there's mutual interest between the private partners that come in and supply some funding and some expertise, and then the academics that team up over the course of the program. So deep learning meets deep science and bringing new synergies for areas of research that NASA is interested in. So this was conceived by the Office of the Chief Technologist at NASA headquarters to explore the applicability of AI and ML to NASA research priorities, how we can get interdisciplinary teams working on short time horizons, and the ability of public-private partnerships to accelerate these sort of better, faster, cheaper objectives that drive a lot of what NASA does. So partnering with early career PhDs in AI and ML, early career PhDs in space research, and then getting these mentors in AI and science, subject matter experts, NASA stakeholders, industry partners, and academia. It's a real kind of fun sort of startup culture program, an 8-week summer research accelerator, which leverages these teams for an extensive sort of summer workshop, kind of hack fest, and runs from late June to late August, starting with a boot camp at NVIDIA, ending with team presentations at Intel, and again, driven sort of out of Mountain View, California by the SETI Institute and its presence there, and the NASA Ames Center. So some examples of some of the topics here: modeling of asteroid shapes, finding long-period comets, forecasting solar behavior, enabling autonomous navigation for exploration, and dealing with the sort of the deluge of data that we have to deal with in modern science and engineering. SETI Institute was selected to host and administer the FDL program because of the history of the Institute supporting NASA research, existing cooperative agreements, proximity to and relationships with the NASA Ames Research Center in Silicon Valley, and the ability to engage private companies, explore partnership opportunities, and the science mentors to support these investigations, particularly into near-Earth objects and planetary defense. I mentioned grant proposals, so NASA's interested in supporting the search, and actually the Congress just passed the CHIPS and Science Act, and it's interesting that called out in that is that the administrator may support, as appropriate, merit-reviewed, competitively selected research on technosignatures. So even the Congress is kind of realizing that the sort of out in the cold aspects of SETI from a decade or two ago, it's really time to change that. We've had some grants through the SETI Institute. My colleague Anne-Marie Cody at the SETI Institute is PI on a grant that's looking for anomalies in time series data from the TESS mission. There's weird things that you find in data that are not necessarily aliens, and in fact, sort of the last explanation that we tend to go to is, it's probably aliens, right? We want to rule out all the other possibilities first. But there's some interesting astrophysics, some interesting science that comes out of anomaly detection more broadly, some interesting applications, to other areas of research. And so, NASA's back in the game. If you want to put in grants that are actually in this area of technosignature research, the SETI Institute is a great place to do that. But also, it's a great place to bring your GNU Radio proposals. So several of the folks in the project leads for GNU Radio are now running an ARDC grant through the SETI Institute, and you too, can bring your grants. Again, talk to Rebecca; she's the expert on this. We'd be happy to engage with you. So, are we alone? Well, there are a few areas I think where we can work together. Technical development, for example, on the ATA, education using GNU Radio that I mentioned, Frontier Development Lab, proposing for grants, and then any other sort of ideas that you may have. And I think that's my last slide, so I'll be happy to take a few questions. Thanks.
Are there any questions in the audience for Dr. Croft? Yes, over here.
So I apologize if you get this question all the time, but what's your preferred solution to the Fermi Paradox?
Yeah, the Fermi Paradox, which I didn't mention, basically sort of if the aliens are out there, then why haven't we heard from them? I think we probably haven't looked hard enough. I mean, I'm a little bit agnostic as to whether they're out there or not. I think our job is to kind of go out there and put constraints on it. We didn't know of any planets outside the solar system, when I was in elementary school, and now, as I say, we know that there are many billions of them in the galaxy. So it may just be a matter of having the right tools, the right techniques, the right sort of ideas as to where we should look. I don't think there are, large numbers of alien civilizations in the Milky Way galaxy. I think there are some sort of, at the high end, there are some constraints that we already have put on that. But I wouldn't want to go sort of much further than that in saying we've really sort of done a good enough job at this point to rule much of that parameter space out. But we're trying.
All right, any other questions in the audience? Are there questions online? I don't think I saw any. All right, so one more round of applause for Dr. Croft, please. Thank you very much. Thanks. So next we have my former colleague, Martin Braun, who's going to give us the latest skinny on USRPs.
All right, good morning again. So like Steve, I wear many hats, and I just want to make it clear that I'm going to give this presentation wearing my NI hat, not my or my shirt rather in this case. So so this is part of the NI sponsor package. So NI is a diamond sponsor for this conference, and even before I was NI, like Edis Research, like we've been a primary sponsor of the conference like since the first conference in Philadelphia. Like, was it 11 years ago, 12? Like, I can't even remember. So yeah, we've been here. There's a lot of continuity. And basically, that's exactly where I want to start. I want to sort of bridge the gap between the last conference and this one. And last year, we announced our, our current flagship USRP, the X410. It's a cool device, 4 channels, up to 7.2 gigahertz. Try tuning until 8 gigahertz. It can also do 400 megahertz of analog bandwidth, which means 500 megasamples coming out of those channels. It supports an RF SoC, dual 100 gigabit Ethernet if you need that kind of bandwidth. It still has like the embedded features of like the N300 series, for example, and you can do a lot of cool stuff with that. And as a matter of fact, you can see one at our booth over there. In fact, actually, Hayden, can you just wave your hand? So he's our sales guy, and I don't know if Marcus is here. Marcus Unger is our product manager. There he is. So he's someone you can also ask about like roadmap, etc. If you need, quotes or just technical questions, you can obviously ask me, but you can also ask those two guys. So cool USRP, and it sort of extends our portfolio in a great way. So if you look on the left, like the USRP B200 series, lowest cost, but also lowest capabilities. On the right-hand side, the X410 or high bandwidth and high channel count, etc. In the middle, we have sort of various other devices that sort of fill all the gaps in between, like the X310, our solid workhorse, and the N300 series with both the embedded features, and either you have a high channel count or you have like a really good bandwidth and sort of signal fidelity with the N320 series, and our embedded series E310, E320. Like you can, various things are all possible with this line of products. But this is old news. This is what we were already talking about last year. So let's take a look what's happened in the meantime. All right. So I'm going to start with our UHD updates. So UHD is the sort of the software that drives the USRP, like it's the USRP hardware driver. And last year we just started working on the 4.1 cycle, and we had a bunch of new features in there, especially for the X410. And that's something that I just want to highlight here. This is very important. So we released the X410, for sale when we knew we could build it and reliable quality, etc. But it didn't have all everything that we could possibly do with it. Like it was not yet sort of available. So we wanted to no longer delay the actual device. But then every subsequent UHD release added new features. And there's a lot that goes into that, but part of that was just like sort of a tight loop with like various users of our USRPs, and many of you are sitting in the audience. So, you could actually like go to Marcus after this talk and say, I have like a very urgent need for the USRP. Like, could you like, think about doing this or that? And then, of course, there'll be many other requests like that, so we can't make any promises, but that's sort of how we sort of operate here. So we've been like adding features. And then that happened with the 4.2 cycle, sort of added full 100 gigabit Ethernet, at the full rate, improved record replay with the built-in DRAM, better GPIO support. I talked about that yesterday. And then, we just started working on the 4.3 cycle, and we have a bunch of new features in there as well that I'm actually going to talk about later in this presentation. But something I want to also highlight, and it doesn't get enough praise, I think, is, we could do a better job, but we could also do a much worse job at just maintaining the software quality by itself. Just make sure that it runs on all the various operating systems. A new version of Boost comes out. We need to make sure that that works. There's like a lot of like small bug fixes that go into these releases that sort of keep it like healthy and maintainable over the years. And we've been we've been improving this piece of software for a long time now. And so, it's because of things like this, so we don't completely try and let it go stale, and I think that's a good thing. All right. Now, NI is a company, is a reasonably large company, and of course there's many things that NI does that are not SDR related, but even the SDR related teams, so there's like the product R&D team, for example, that's where I'm from, and we actually build the devices and make sure the drivers work, and the GNU radio integration is there and stuff like that. But there are other teams at NI that also work with the SDRs and sort of provide types of products, and that's something I want to talk about in this section. So in particular, I want to highlight two what we call offerings that we have available for people that have specific application needs. Now, something that's popular for many reasons is like doing wireless research, like in the 5G, and then obviously in the future in the 6G, or as as I heard yesterday, like the future G space. So this is a standard picture of sort of a 5G cellular setup. So on the left-hand side, you have the core network, and the control plane and the user plane are sort of the technical terms that we use to describe those. That's usually all software that happens there. On the right-hand side, we have the radio access network. So these are, the G Node B and the actual device, like the UE. That could be your smartphone, but it could be some kind of, dongle connected to your computer. all of these things. So this is just a standard picture of like a 5G setup. But what if you want to start doing research in this domain? You want to sort of like start tweaking individual components. Like how do you actually do that? So we actually have a bunch of, we had a presentation yesterday on, you know, like swapping out individual components using various AI features. But you have to sort of, you know, actually, you know, practically like you find the screws where you can open this. And that's exactly what we provide with this setup. So this is an OAI based setup. So OAI stands for Open Air Interface. It's an open source project that provides 5G. It also provides LTE access. And this is all like open source software based. So this is stuff that you run on various servers. And it's not software that we write as an I. But we are an alliance partner of the Open Air Interface Alliance. And so we can provide sort of a full end-to-end setup using USRPs, obviously, but then also like various other you know, components in there. And because this is end-to-end open source, that means you have all the hooks and, you know, hatches available to open and see inside and modify. And you could always do that. I mean, even USRP1 had like GSM-based things running on top of that. But what's different is that we have the sort of dedicated teams that sort of make sure that this entire stack is running, and you can sort of approach us as an I, say, hey, I want to do this. I want to do 5G research using the stack. Can you get me, you know, set up, etc. And that's precisely what we can offer now. But outside of the 5G research, we also like working with folks in the doing, for example, radar or EW, electronic warfare research. And the requirements there are not exactly the same. So with, you know, the 5G system, you want to be able to actually do phone calls, etc., and then start playing around. If you're doing radar research, typically your requirements are a little bit more low level, but you also have higher requirements when it comes to channel count and bandwidth, etc. So I imagine you actually want to do radar signal research, something like that. What would you need? So you would probably need a lot of channels, high bandwidth. Those channels need to be phase aligned, so they need to be phase coherent, need to be synchronized. And then you want to stream all the data somewhere, so you need like a bunch of computers to capture all of that, or maybe playback, so you want to do record and playback kind of setups. There's, you know, and then to get that all running, you need a whole bunch of software, you know, the correct driver versions. There's probably like an optimal operating system version or kernel version. You need a lot of documentation to get that started. Maybe, you know, the actual cable matters that you're trying to use. And all of that is sort of something that we sort of bundle up in this specific offering. So if you're in this domain and you care about you know, setting up sort of a, you know, many channel count, high bandwidth research platform, then that's something we can offer. And just to give you some glimpses in what that actually entails, is there's a lot of documentation. Again, there's sort of a dedicated team that sort of manages that, provides reference software as well. So if you go to our booth, you can ask about that, and like some of the people maintaining that are actually sitting at our booth, and they can answer all the questions that you have. You know, down to like which rack you should be using, just like details on the setup, like that's all provided in this sort of package, nominal specs. And this means that you can, you don't have to sort of worry about like the boring stuff, like, oh, like I have to do with the sysctl blah blah command, yada yada. So like that's all taken care of by this documentation, etc. And you can just start streaming and start researching, etc. Okay. Now, I mentioned earlier we have a bunch of new features in UHD that we've been working on over the last year. And I want to highlight two of these because I think they're really interesting. The first one is the UHD Extension Api. And now I need to rewind a little bit. I need to sort of provide some background here. So we often get requests for specific RF specs, right? So for example, someone might say, oh, I want to do 5G, but like I can't just use like a general purpose SDR because it doesn't neatly fulfill our, I don't know, spectral mask requirements, for example. And you know, we can handle that. We know how to handle spectral mask requirements, but we can only handle one type of specs at a time. But we don't, on the other hand, we don't want to sort of break the general purpose nature of our SDRs. And how do we resolve that conundrum? Well, sort of the the idea that we have here is that extensions are a good way to make that available in a modular fashion. So we could say, well, the USRP stays general purpose, but then if you need specific spectral mask requirements or power requirements or anything like that, then you add an RF extension, is what we call it, on top of the device. You can see just a rendering here, what it could look like. So at the bottom you'd have a USRP, and then you have like short analog connections into your extension and maybe some digital control signals. And that way the other box can take care of the the RF requirements. So that's what we call an RF extension. And the extension API is an easy way to enable that without breaking your software workflows. So what we want to avoid is that you put on this extension API and then you have to like compile against yet another library, and then there's like this other manual and yada yada yada, and you have to like restructure and refactor your applications. That would be annoying, because the intention is that we add these extensions so we have like the same USRP be more flexible. We don't want to make the software more complicated at the same time. Excuse me. All right, and that's where the extension API comes in. Now, we didn't just write this extension API out of thin air. So there was a reason, and so we teamed up with another company called Signalcraft, and I know we have at least someone from Signalcraft here, Bernie. I don't know if you're in the room. If you are, then you could raise a hand. Okay, I can't see him right now, but we have someone available. So this is a company that we partnered up with, and they built this device, the Sc2430 Rf Extension. So it's called the Sc2430 New Radio Signal Conditioning Module. And as you can imagine from the name, this is specifically designed to achieve like the RF requirements for 5G New Radio. So if you want to build UEs or there we are. We have Bernie over there. Hey Bernie. So you can ask him questions about this specific box. You can also see one of those at our booth. Some more details. So again, like I showed you earlier, you would sort of put it on top of an X410. You would cable it up with like short analog connectors and short digital control connections, and then you get 5 GNR compatible signals at the output. And a couple of more details here. So so this is sort of a high level block diagram, what's going on the inside. You can see it contains a bunch of filter banks and amplifiers, etc., switches, and it lets you tune those filter banks, etc., such that you can achieve the required spectral mass for these specific bands. And going back to my own slide deck now, you can see like if you actually wanted to just get started with that, the only thing you would have to do is like add a string in the initialization sequence for your device, as you can see here, to sort of notify UHD that you want to use this RF extension. But you don't have to like load different drivers, etc. That happens all in the background, like through some transparent DLL loading, etc. Of course, you need some software available to do that, but you don't have to change your applications. That's the key thing. So the other thing I want to talk about is raw UDP traffic to remote destination feature that we've just released. This picture is sort of a standard streaming setup. So you have a USRP, and it has like what we call a radio. That's the thing in the USRP that captures signals, and then eventually it'll get pushed out over the Ethernet connection. And then on the other side we have UHD, captures that traffic and then makes it available to the application, for example, into GNU Radio. Now the thing that we added is that you can sort of redirect the traffic and send it somewhere else. So especially when you're in a network situation, you can just go to UHD and say, okay, like I want this frequency, I want this gain, all of that stays the same. But when you're finished setting it up, I would like all this traffic to go to a UDP port on that network address, for example. And and this is something, looks pretty simple at first glance. The key thing that we try to make get right is the sort of coherent integration into the rest of RF NOC. Make sure we don't break any paradigms, etc. And that's what we did with like sort of the latest. If you look on Master Branch, you can play around with this feature. So it's not actually in the 4.3.0.0 release that just came out, because we just missed sort of a merge window there. And the X310 support is also not yet on the public Master Branch. We have like a minor glitch to fix there, but we've seen it work. So just to sort of give you an update on that. So whatever the next UHD release will be, we'll have that feature built in. So what can you do with that? Couple of things. So this gives you a lot more flexibility when it comes to streaming. So before, if you were running a UHD session and connecting to multiple USRPs, all of the USRPs would send the data back to the same UHD session, which is running on a single computer. That sort of limits your available streaming bandwidth just on the software side. And that's gone now. You can just like stream data wherever. And if you're sort of in a, you know, arbitrary topology, you can stream data left or right, wherever it needs to go. But you never sort of leave the paradigms of RFNOC. Like you can always like, you know, reuse everything that you've been using in the past. For example, if you wrote some custom RFNOC block. If you want to send raw UDP traffic back to the USRP, that's something we have on our roadmap, but not in the near future. This is slightly more difficult for various reasons that I don't really want to go into right now. But yeah, there's something we have on our agenda. And one thing you could do with that is you can actually take the data and modify it on the USRP before you start streaming it, blasting it out to the to you know, whatever your endpoint is. And one thing you can do is you can say, oh, I'm going to take this data and turn it into Vita49 frames and then send it out. Now we have two modes of streaming, or at least two modes. We have a few more. There's some subnodes, etc. But like two things that you can do with the traffic that's going out is you can enable or disable our own packet format. So our packet format is called cheddar, and you can say I want to keep the headers of those cheddar packets if you know how to interpret them. You know, we've documented that. But that's extra work on your end. You might not want that. You can also say I just want to have the raw payload. But if the raw payload is a Vita49 frame, boom, you have a device generating Vita49. And as a matter of fact, our friends at Microsoft did exactly that. So this slide is also, again, this is not my slide, this is from Microsoft. Thank you very much for providing that. What they would like to have is the ability to do exactly this in satellite ground stations. And the specific Vita49 dialect that they use there is called Diffie. So they built and open sourced an RFNOC block that generates Diffie frames. And in combination with this like feature of the ability of sending your frames wherever you like, you now have a digitizer running in your satellite ground station that can speak to other Diffie compliant devices. So that's really neat. All right. Okay. So that's what we've been doing. So we sort of caught up in time now. I've brought you to like, September 2022. But I do want to give you a bit of a glimpse into the future now at this point. So actually, I'm a bit ahead of time here. I hope you have some questions. Oh, that's not right. Tom can always fill the gap. Where was I? So, glimpse into the future, future roadmap. And this is where I always get a bit nervous, because that means I have to, once we show this stuff, we of course have to deliver it. Yeah, but here we go. So I showed you a whole bunch of things that we've been working on. So as the UHD side, we've been adding features every release. We've been fixing small stuff as well, but like a lot of new features like the extension API, raw UDP streaming. RFNOC streaming is actually pretty capable these days. You can do multi-gigahertz streaming with RFNOC. It's not something, the X410, for example, you would have half a gigasample as a max rate, but RFNOC is capable of doing that. And we have like 100 gigabit Ethernet to support that as well. So what if UHD is too slow? No worries. We have we have our raw UDP streaming improvement. And then of course we have all those system design, system offerings that we have to offer the, I mentioned earlier, like the 5G, 6G research setup, and also the, radar EW research setup. So we have all of this stuff going on at NI. So what do we do next? And, it kind of feels like we need to build another device, another USRP. So that's what we did. So we, I'm proudly, like for the first time, introducing our next USRP. It's not available yet, slated for early next year, the X440. You can see like in the rendering at the bottom right, this looks a bit like an X410. And that's because we are using the same, the same chassis and the same, like a similar motherboard. It's not exactly the same. But what's different is that we're going up to 8 channels now, and also higher bandwidth. So channel bandwidth, at least gigahertz of bandwidth. We can't actually fit that many SMA connectors, so we had to go down to MMPX connectors, as you can see. Yeah, but it gives you a whole lot of bandwidth available for all sorts of applications here. Now, how do we do that? Now, this is where the extensions come in. We actually removed a whole bunch of analog circuitry, and we are now using, because we can have these high data rate, high converter rates on the RF SoC, we can actually use direct sampling here. So there's no mixers on here, but that also makes it a little bit easier for us to achieve phase coherency. So you can run the converters up to 4 gigahertz. You can use 2 Nyquist zones, which means you can go up to at least 3.6 gigahertz of analog frequency if you run at a 4 gigahertz sampling rate, and that already gives you like a lot of capabilities. Of course, it's because it's X410 based. We have all the features that we had in the past, like 100 gigabit Ethernet. You're probably gonna need that if you want to stream out that amount of data. But the one thing that we did change is we switched from speed grade 1 to speed grade 2 because it's going to be really important to be able to hit those high rates when you're building bit files. Yeah. Who's gonna? Oh yeah. I just wanted to prove that we're actually building this. Here's a picture from the lab. Not entirely complete, but this is what our software guys are working with right now to make it work. And you can see all the LEDs blinking, etc. So it's a real thing. It's not just vaporware. And so what can you do with it? So because it's a direct sort of sampling architecture, like basic RX, like in the past, like you probably want to at least use some kind of filtering if you want to connect it to whatever your application is. But what's also likely is that you would use some kind of external RF extension, maybe for up and down conversion that would give you like all the frequency ranges that this can't hit otherwise. And I think like a great use case for this is in satellite ground stations, because operators of satellite ground stations, they know their RF, like up-down conversion filtering. That's something that they know very well. So this might fit in just pretty well. It has high bandwidth and a lot of channels in a small form factor. But really anything that requires high channels, high bandwidth, and you can use some kind of filtering. This is definitely useful application, a useful device, I mean. All right, I'm gonna leave a little bit of time for questions, and then we're gonna go over to Tom, who will introduce the keynote. But I just want to sort of summarize what I spoke about. So we have like a long continuity here, like coming from our sort of lower cost devices up to the X440 that I just talked about. Because we have this, because we have this, with this broad spectrum of devices, we can fill a lot of gap. We can fill a lot of applications, a lot of niches here, and provide the right hardware. But we also have like sort of systems folks that sort of work on putting it all together. And of course, we're still making sure that our software works on all the various operating systems, etc. So we want to try and keep that running as well. So yeah, I think we're well set up going forward, and yeah, I'm very happy to take your questions for the next few minutes. Thank you.
All right, it is great to see that UHD continues evolving even in my absence. Any questions for Martin? Yes.
So you've got the Nyquist on the 440 at 1.8 gigahertz. Is that tunable? Because a lot of the L and S band for downlinks that you're talking about going after cover 1 to 2 gigs. So that's going to be right in the middle of a lot of the downlinks. So is that a tunable parameter? Or are you guys going to look into extending that out to a further than 1.8? Because it's right in the middle. So
it's not only tunable, but also that's a new feature. It's separately tunable on 4 sets of channels. So you can have two different Nyquist rates, and that way you can actually cover, you can even cover like the entire range. You can just like choose a different Nyquist rate on like a different set of channels, and then you don't have to like touch that annoying gap in the middle where you have to sort of switch between the Nyquist zones. Yeah, it's a great question. I should have said that.
All right, got another question from the audience.
Thank you. So GNU Radio is a great tool. I love using it. The problem that I run into, thank you. The problem that I run into is the use cases and performance of new blocks, right? So you're adding raw UDP, you're doing these things. Are you going to have use cases, what it extends to, how far it goes, and what it actually does for your system? And in a broad sense, that is, are you going to show performance capabilities, and are you going to show where this wouldn't be useful, I guess?
So yeah, I guess what you're hinting at is like we give you like the raw bandwidth, but like we leave you like to deal with it. So yeah, we definitely going to show like sort of performance. You know, we're gonna grab a gigahertz of spectrum and then show that that meets the requirements. You know, you mentioned GNU Radio. Like GNU Radio won't be out of the box able to handle like multiple gigasamples worth of streaming, and you know we can't solve that just by releasing the X440. But I mean, one thing we have been doing is providing, for example, RF integration for GNU Radio, so you can do pre-processing on the device. In this case, it's not clear how much processing power we will be able to put onto the FPGA, because like just running 8 channels already takes a lot of, you know, real estate on the FPGA. But assuming you could leave some space, then you know that would be one way to solve that problem, where you just basically do some pre-processing on the device, and also, you know, if you stream out of 100 gigabit Ethernet, it doesn't have to go straight into GNU Radio or another computer. You can, for example, move it into, you could have an FPGA card with 100 gigabit Ethernet and do more pre-processing there. You know, there's ways to deal with that. And we also have like, you know, partners that have like just very capable software who, you know, who think they can actually work with these rates. But you know, GNU Radio 3.10 is not one of them. I admit that is true. But you don't have to run it at you also don't have to run it at like a gigahertz, right? You can also run it at low bandwidth, and you still have like the large number of channels. And then GNU Radio comes in handy again, because you can distribute your channels onto various compute nodes, and you know, do something with that. I don't know. I think I gotta. So Marcus is raising his hand, but I think I gotta get to a timeout now.
Thanks, Aaron. Just to quickly to add to that question, this device will be used as the next evolution for the reference architecture that Martin was showing earlier for the radar and EW research. So that is going to be a practical example of how to use it, how to dimension your surrounding systems, what kind of IOs you need, that kind of stuff. And we're going to benchmark it, like how many channels with what kind of bandwidth can you do there. So yeah, you're going to have practical examples of what you need to get it running in that capacity.
I think that's all the time we have for questions. So thank you very much, and we are available for more questions offline. Bye.
All right, thank you, Martin.
All right, well, Josh is getting that up. So hey, everybody, Tom Rondo again. Maintained GNU Radio for about 6 years before I moved to Darpa, and spent 6 years there. I'm now depending on running our future G and 5G efforts. And I am thrilled today to be able to introduce Dr. Stephanie Tompkins as our keynote. She's the director of DARPA, the Defense Advanced Research Projects Agency, where she is a legend for the amount of time and effort she has put into that agency and using that to help secure the United States. She spent time as a program manager, as an office director, and now she is the director. And I'll say, before I let her really take over and explain what she does at DARPA, what DARPA means and what it does and what it can mean for this community, I want to explain what I've always appreciated about Stephanie and her role and how she approaches her work. DARPA makes very hard, fast decisions about how to develop breakthrough technologies for this country. She is willing to sit there and spend the time to listen and take in all sides of an argument and all the inputs that are necessary, but she's never hesitant to make those hard decisions quickly when they need to be made. So her ability to go from passive listening to active, let's get stuff done for the country, has always impressed me, and her ability to maintain that for the amount of time that she has spent doing this work for us. So with that, I will introduce Dr. Tompkins.
There's the ritual lowering of the microphone for my height. It's better? Okay. All right, so good morning, everybody. I am thrilled to be here. And as you'll quickly learn, I love to talk about DARPA. So you may have to raise your hands in defeat if you're getting a little too much from me. I did plan to make sure that I've got time for questions from you, though. So my goal today is to give you kind of a glimpse of what DARPA is up to in areas that we think you might be interested in. I'm also happy to segue into anything else we're discussing, but I'm going to start off by giving you a little bit of a kind of a DARPA 101 to help put everything that we're doing into context. And then I'll dive into, kind of a panoply of different communications-related programs that we've got underway. So, to start off, DARPA was started in 1958 in response to what was, at the time, a really big strategic surprise for our government, and that was the launch of the Sputnik satellite. From what I understand, as often happens within scientific communities, it wasn't maybe quite as much of a surprise, but the politicians were upset, and they vowed that this type of surprise should not happen again. And they did a number of things. Among them, they created NASA. And then they created this little agency called the Advanced Research Projects Agency, which was designed to create technological surprise. So it's kind of hard to avoid surprise in the sense that we don't have the magic crystal ball yet. But the idea was that if we could be technologically leapfrogging ourselves, then we would have that chance of being the creator rather than the recipient of technological surprise. So we've been doing that ever since. I think we were lucky to have started in a time when the government was a much smaller organization and a little less bureaucratic. The original agency had a lot of freedom and flexibility, and as they moved through time, they kind of had enough success to earn the freedom and flexibility that we have been able to maintain ever since. So our mission is to make pivotal early investments that change the trajectory of technology, and we do it across pretty much every imaginable technological field, and maybe even not so technological, because we're starting to move into social science, which is really hurts my head. But if you look at this timeline, there's sort of two categories of things to think about in terms of DARPA's greatest hits. On the top, you'll see systems. So these are big military systems, including a lot of the early work in communications and networking. Of course, stealth aircraft, uncooled infrared night vision, miniaturized GPS receivers, and other forms of precision guidance and navigation, unmanned aerial vehicles, things like that. On the bottom, think of the enabling technologies. This is like university work, a lot of small companies. A lot of the kind of work that I would imagine folks in this audience like to think about. So we invented material science as a discipline. That's a little bit of an exaggeration, but basically before DARPA, you had metallurgists and chemists and maybe mining engineers all running around not talking to each other a lot. And we sort of forced them all together. And that led to a lot of really breakthrough work in different kinds of metal alloys, composites, and of course, semiconductor materials. Information technology, you might have heard of this little experiment that DARPA conducted called the Arpanet. That grew up and graduated to become NSF's research network, which then, with the help of politicians, and I have to tell you this, that includes Al Gore, the legislation went into place to turn it into the internet, which we know and love and maybe sometimes don't love so much, but it's kind of a good example of how DARPA works, because we made those early investments to change what was possible, but it was really a much bigger community and ecosystem that turned it into what it was. We have been working on AI since the beginning, and as you can see on those timeline bars, there are a number of AI winters where we stopped, waited for the technology to kind of become interesting again, and moved back in. Of course, we wanted to make sure we highlighted a lot of our early work in the underlying technology related to software-defined radios, work in microelectronics. We did a few really interesting competitions. By the way, the hissing is driving me crazy. I hope it's not driving you crazy. If you're okay, then I'm good. To challenge self-driving cars in a race. The very first one resulted in some fantastic crashes and flaming wrecks. Not a single vehicle crossed the finish line. but my predecessor demonstrated the kind of courage that I hope that I will always be able to have, which is going in front of the news reporters to report that we had utterly failed and we were going to do it again the next year. And the next year, multiple vehicles crossed the finish line. A few years after that, we made these self-driving cars operate in urban settings, and the winners of those vehicles pretty much all got hired by Google, and thus the self-driving car industry was born. Whether this is a good thing or not, I'm not sure. We are responsible. We're directly responsible for Siri through a program that was originally called Personal Assistant That Learns. And most recently, and I think it's a good thing because it's a little bit of the reason that we're all physically able to be in this room, those of you who are here, is an investment about 10 years ago in vaccine technology. We had an Air Force officer, a medical doctor, who was really worried about the fact that we send our service members all over the world, and they're vulnerable to all kinds of diseases for which they have no immunity. And the methods we had for making vaccines were just ridiculously slow for what the military needed. So he started a program that invested in nucleic acid-based vaccines, including messenger RNA. And there was this little company called Moderna, which you might have heard of, that was one of his earliest performers. So I went through that to try to give you a sense of kind of the breadth and the depth of how DARPA works. We are very, very risk tolerant, and I think it's worth mentioning our business model. Tom talked a little bit about being a program manager. The heart and soul of DARPA really is our collection of program managers, and at any moment in time, we have about 90 or 100 of them, and they come to us from all walks of life, strong technical experts, but they can be academics, they can come from industry, they can come from other government labs. We're even starting to explore the idea of potentially having one or two coming from our allied partners in countries like Australia or the UK. They come for a temporary tour of duty. While they're with us, they have access to a $4 billion budget, and they're told to change the world, but they only have about 4 years. And so if you've worked with DARPA program managers, if you've worked with Tom, you know there's a little clock ticking in the back of their head. There's this sense that I get to change the world, but time is running out. And so they will go out there and they will fund lots of things fairly quickly in order to assess the landscape. They will start big programs with the understanding that they might fail, because it's a lot faster to try something and fail than it is to spend months and maybe years thinking about it and trying to overanalyze, all the things that could possibly go wrong. So that's the context of DARPA. What I'm going to talk about now really is the far right. We don't spend too much time on the past because really we're thinking about the future. That's all my program managers care about, and that's what we're investing in that maybe a successor of mine a decade from now might have the opportunity to brag about. So these bubbles show DARPA offices. I'm always a little uncomfortable about DARPA offices. We have 6 of them. And I tend to think of them as homerooms for our program managers, because really the fundamental unit of action in DARPA is the program manager. Within the offices, they receive administrative support, technical support if they need it, mentoring, obstacle removal. But we don't organize our offices in such a way that they are not designed to tell the program managers what to do. But nonetheless, I have 6 offices, and 3 of them are highly relevant to today's conversation. One is the Microsystems and Technology Office, which is focusing very heavily, as you can imagine, on microsystems. So think of them as the hardware space. And we've got some themes that they've been focusing on, including directional and millimeter wave technologies, a lot of new work in smart devices and components. And I'll highlight some of those in a minute. Our Information Innovation Office lives and breathes software. And for today's conversation, it'll mostly be about software security, but as you can imagine, they are deeply involved in AI and machine learning techniques and trying to figure out what the next wave of artificial intelligence really is, because they are convinced that machine learning is nowhere near what we actually would need to solve problems where we could put any real trust into devices. As you can imagine, in the military, we have to trust our software with our lives. And right now, it would be foolish to do so with purely statistically based machine learning techniques. And then at the bottom, we have our Strategic Technology Office, which is a systems office. So they will often be putting together things that come out of offices like MTO and I2O into these bigger systems or even systems of systems. So what I'm going to do now is I'm going to kind of take you on a tour. Think about starting in the upper left corner. We're going to focus on hardware. and how that might apply across the military national security domain, so the battlefield in this particular case. Then talk a little bit about security, both software and hardware, and then we'll move into talking about systems. And then I'm just sort of plucking random programs out based on feedback from Tom and some of his colleagues into what we thought might be of great interest to you. But of course, I'll be happy to answer questions on things that I might have missed. So, it's really hard to give a Department of Defense talk if you don't have one of these, what we call OV1s, overview charts, with lots and lots of lightning bolts. And at least, since this is related to communications, those lightning bolts are actually kind of relevant. They look a little weird sometimes when people are showing like underwater pictures and things like that. So what I want to say is that each one of the things you're seeing is a DARPA program. The fact that each one is like right next to a platform is utterly irrelevant. Okay, so any one of these things, for the most part, could be on a satellite, an aircraft, a ground vehicle, or even a surface ship. We didn't have the artistic skill to figure out how to get the ocean in there at a reasonable scale. With one exception down at the bottom, the DEPRIVE program, which I'll talk about, one of Tom's babies, is not likely to be operating in real time on any of these field systems. But just to highlight a couple of things, the MIDAS program, for example, the title, the little description sort of says it, millimeter wave multi-beam digital phase arrays. This is a program that seeks in the next few years to be able to demonstrate a 256 element array operating with multi-beam functionality across the full range of 18 to 50 gigahertz. Lots of hardware miracles have to happen before we can actually get to that. ELGAR at the top. Again, arrays, focusing this time particularly in G-band, 110 to 300 gigahertz. Again, lots of hardware challenges that have to be overcome. And there are several other of these I'm going to highlight with a little more detail, starting off with that tour of security-related topics I mentioned. So we're going to talk about SIF and GAPS next. So SIF, System Security Integrated through hardware and firmware, that acronym just does not sing to me. So we just go with SIF. But SIF kind of operates on the assumption that both software and firmware attacks are typically exploiting some vulnerability in the hardware. And so the whole point of this program is to go after these fundamental hardware vulnerabilities and close them off. So these might be things like buffer errors, information leakage, incorrect sort of permission spaces, system of sort of implementation errors and things like that. So the idea being that if you can close these off within the hardware and actually in the chip design, you're eliminating entire classes of things that you would have to worry about doing software security updates on. SIF was pretty confident in its capabilities. They actually ran DARPA's first ever bug bounty. It was, so you're going to love this, finding exploits to thwart tampering or FET. And I think there were a whole bunch of other sub-programs in there that have connectivity to kind of the SIF and FET theme there in terms of what they named things. But it was 3 months, over 580 security researchers were attacking these sample systems to try to find weaknesses, and none of them were ever successfully exploited, and only 10 vulnerabilities were actually found over a 3-month period of prolonged attack. So it does give you the sense that if you know what you're doing, you can actually design hardware in such a way that maybe the software people can not have to be quite so precise and careful about what they do, what you do, right? So potentially make your job a little bit easier. GAPS, Guaranteed Architectures for Physical Security, has kind of a similar set of goals, but this really focuses on physically creating within the chip itself kind of air gaps. Or in other words, you want to physically cordon off that parts that you want to keep secure so that you can have both unsecure and secure levels of processing happening on the same device. So it's just a different technique, but it was different enough and unusual enough that it kind of merited a separate program to do a deeper dive. Now, if we think a little bit on the software side, and this might be a little closer to your heart, we'll talk about our Open Programmable Secure 5G or OPS 5G program. So I think this one, the diagram is relatively self-explanatory, particularly for this audience. Right now, you've got an opaque integrated software hardware system, lots of proprietary information. DARPA is focused on working in partnership with the Linux Foundation this secure and open source development environment. And the program itself consists of lots of companies and academics, basically what we call performers, exploring the space of what you can create in software that can get us to this bigger vision of a much more open and a fundamentally much more secure capability. We have a brand new program on the right called Gecko. The broad agency announcement is on the street. This follows the similar theme of Ops 5G in the sense that we in the DoD want to take advantage of existing commercial capabilities, but we need to provide the security that makes it usable for us. So Gecko is focusing on creating these communication channels on unsecure networks that would allow privacy protections for the users. And that, as you can imagine, there'd be very interesting and useful commercial capabilities as well if we're successful in making that work. But if anyone is interested, proposals are probably due in about 2 weeks. And even if you had known about it before it came out, you would have only had 45 days at the most, just so you know. Everything about what DARPA does tends to be accelerated. So if you're interested in any aspect of this, what I strongly recommend on any program I talk about is to go to our website, get the name of the program manager, and go talk to them. Because even if the program is already underway, you might learn about something that keeps them up at night that is relevant to what you do, and you might be able to kind of separately design a new concept or a new thing to sort of explore together. All right. Now, next OB1 chart, but it's also the last one. These, and no lightning bolts. This is going to think a little bit more about modalities. So not just about the devices that are being made. Oh, and actually one thing I forgot to mention, on that last one, when you saw all of the little satellites and aircraft and the systems there, that is very much tied together to something that we've got underway called the Electronics Resurgence Initiative. So about three and a half years ago, we recognized that, one, we had sort of managed to offshore almost all sort of semiconductor manufacturing capabilities, which is not a great supply chain situation. From a national security perspective, that's not great. And of course, from all the other issues related to chip supply chains that I think everybody has been dealing with, it's not a great situation. That is something that obviously the Chips and Science Act and other things that are happening are supposed to deal with. DARPA's role is not to solve that problem. Our role is to figure out how to go to the next generation and kind of out-innovate what's kind of happening everywhere else. And so fundamentally, we tied ourselves to Moore's Law. We were all fairly convinced that without a significant change, well, I mean, we knew that without a significant change that we were going to be plateauing and you were not likely to see any processing improvements in the coming years. So we made a series of big bets to look at what came next. As a result of that, we were focusing on security, we were focusing on new materials, we were focusing on being able to process at greater speeds at the edge, kind of at the battlefield edge. But as a result of that, I think we are sort of all in on 3D heterogeneous processing, heterogeneous chips. So completely different materials stacked together, moving vertically. So we can run out of room horizontally. We've already run out of horizontally, we're sort of stacking. But this tremendously hard problem of working across different materials that were never designed to operate effectively together. So most of the programs you saw on that past overview chart are tied to that original Electronics Resurgence Initiative. We are kicking off ERI 2.0, where we're going to focus on manufacturability and real-world environments. So in space, deep sea, high pressure, radiation, whatever situations might have. So that leads me into this topic because, in the Department of Defense, we do have to think a lot about not just free space. We think about underground, we think about operating underwater, and we tend to be thinking about things that have to cross a lot of different domains. So this is a little more focused on a couple of different themes. One, gateways that would enable different kinds of systems to work together. Just as before, with a couple of exceptions, where the little program names are relative to the drawing doesn't matter that much. The two where it does matter, I'll talk about in more detail in a minute. But the bottom line is we need to have everything, as flexible as possible. We need things in the smallest possible form factor with the greatest possible performance. And that, if you wanted to just design an imaginary DARPA program, you pick whatever it is, and your goal is to make it 100 times smaller, 100 times faster, and figure out what technical miracle you would need to achieve to get there. And if you could also have it use no power, that would be even more awesome. So, yeah. So that's the common theme. But here, to highlight, a lot of what we've done is looked at kind of physical and software-based gateways. So Dynamo, right there in the center, that's a program that allows, for example, our Marines and our Army, who you would think would have radios that talk to each other, actually talk to each other because their networks inherently don't talk to each other, right? So these are software solutions to be able to make those connections. The success of Dynamo led to the birth of a program called Mink right below it, which is really looking at this kind of network of networks optimization path where it is constantly tracking all of the networks available and figuring out optimal routing of any communications or any information that needs to move across them. And I think I've got a picture in a couple of slides that will give you a better idea of what that looks like. So let's do that, and let's talk about first a couple of these domains. Remember I mentioned there were a couple of things where it actually did matter where they were on the chart. Timely is both underwater and in free space, and Space Bacon is focused on outer space. So these are things that might be of interest from a sort of a software radio perspective as we move into these new domains. First of all, when I say Space Bacon, did anybody chuckle? Do we have? Okay, so it's not just an inside joke for the Air Force. This is an homage to an existing system called the Battlefield Airborne Communication Node, or BACN, which fundamentally acts as sort of this gateway between all different kinds of RF systems. That was also initiated by DARPA, by the way, back in the late 90s. And so Space Bacon actually stands for something slightly different, but it's the same basic idea, only for optical systems. And if you've ever spent time thinking about the fact that you've got all of these different commercial networks of proliferated low Earth orbit satellites going up, you might have wondered, were these companies talking to each other and designing their systems so they could interact? And if you've been around for more than a year or so in this world, you know the answer was no. And sure enough, the DoD was thinking about our own systems, which would have yet another different set of modalities. So Space Bacon is meant to create these optical gateways that will go up there and connect all of the different low Earth orbit communication systems. Space Bacon, by the way, also was a fun opportunity for us to try to innovate in being able to get more commercial companies that have never worked with the DoD involved in helping solve our problems. So for any of you that have sort of felt like there is this immense barrier to entry, we've got a lot of people in this domain that are working at ways to sort of knock some of those down. And I'd be happy to talk offline for anyone who might be interested on things that we're initiating in that space. That includes access to classified work, even if you've never had a clearance before. So hopefully that's exciting. It's definitely exciting to me because, as you can imagine, it limits our choices and our ability to solve hard problems if we can only go to the small handful of people who are already on the inside. So that's Space Bacon. Timely is really focused, the cool part of Timely are those little UUVs that you see down there. They sort of drift up and down, and they're broadcasting across acoustic channels, and then they're getting and receiving information from RF. So the idea is that if you have a whole network of these sort of bobbing up and down at different times, at any one moment in time, one of them is up where it can hear, and then it goes back down and it's transmitting across the acoustic space. So, but I don't think Tom mentioned this. By training, I'm a geologist, so RF way too fast for me. Acoustic is at least starting to get into that slow mode. Now, when you move into geological time, then I'm with you, right? So millions of years. But we're very excited about the fact that with Timely, you could actually broadcast across a large acoustic area on the order of a few hours, which doesn't seem super fast, but if you are used to living underwater, it's way better than the speed of light, right? So there's a lot of excitement about being able to do this. So. Okay, then I promised I would come back and talk a little bit about Mink, but I don't think I have to say a whole lot about SDR 4.0. This was, this was one of your inventions, right, Tom? Right, but really focusing on kind of the GNU radio scheduler and optimizing it to enable a whole bunch of new capabilities. So we're excited about what that does community-wide and specifically for a lot of our programs. And then here's that layout of the MINC program. So the idea is that you might have space, air, ground, sea, networks. This is then creating that network of networks where it's keeping track of everything out there and then optimizing whatever communications path you need to get information from one point to another. So it builds upon some of the successes from that Dynamo program. All right, and then you've been very patient. I just have two more I wanted to talk about. My talk is a little bit of an homage to Tom Rondeau because Deprive is also his program. You started it, right? Yeah. So this comes down to talking a little bit about security. How many people here are familiar or have ever tried to write algorithms dealing with fully homomorphic encryption? Okay, so fully homomorphic encryption, this is basically mathematics, and the idea is that, you know, in the typical world, if you want to protect your data, you can only protect it at rest, right? When it's sitting somewhere, if you want to actually operate on it and you want to do something with it, you have to unencrypt it first. And that's kind of not what we actually want. So with fully homomorphic encryption, you can actually operate on encrypted data. So you can imagine this could be really useful in the banking industry. It could be really useful when you have different partners working together who want a shared outcome, but they may not want to share the real core secrets of their own intellectual property. From a Defense Department perspective, this could be a kind of situation where we're working with a lot of allied nations. And again, we want to be able to present integrated defense capabilities, but we're not quite willing to share the secret sauce with our partners about how to do that. Can you do a calculation that would talk about whether or not your overall system has the capabilities that you need? So this sounds great, and we actually had a program a few years ago that went all in on developing new algorithms and kind of focusing on the underlying mathematics. The problem is that to solve any practical problem, you would need at least weeks, maybe a lot longer to get there. So Deprive was focusing on the hardware accelerator part of the problem to say, what could we do to actually make this practical? We're not trying to get to a point where this is going to be a chip in an aircraft flying somewhere. What we're trying to do is get it so that that calculation time goes from weeks down to seconds, so that it actually becomes usable and practical for certain classes of problems. But for those classes of problems, this feels like a huge game changer. And very, very, very hard to do. I think the bets are still out as to whether or not we think it's really going to make it or not. But it's absolutely worth it. And early successes caused us to kind of double down on it to see where we're going to see that we can actually help get it across the finish line. And then on the very first, that kind of overview slide, you might have seen down in the corner domain-specific system on a chip. So this is another thing that might be of interest to you all in terms of sort of hardware innovations. This is focusing on kind of finding that sweet spot in between general purpose processing and specialty processing. And the idea is that you're going to create a whole bunch and combine different processors that might operate usefully across a domain. So they're customized and optimized for a certain class of problems. But then within that class of problems, you have all kinds of flexibility and programmability in order to work on individual applications. So I think within that, not just with the hardware, there is a whole tool stack that they're working on in order to make sure that users have and programmers sort of have the flexibility to do that kind of hardware-software co-design. I should mention, I think that's also an interesting aspect of Deprive as well, which is that it's not just about creating the hardware in a vacuum. It is about co-design from a hardware, software, and algorithm perspective, because you really need to have all of those optimized across each other. Okay, so I have just take advantage of the fact that I have you as a captive audience to come back to the bigger DARPA story, do a little bit of a shameless plug for a series of activities that are underway right now. So give me 2 minutes of your time before I take questions, and enjoy this.
Coming to DARPA is like grabbing the nose cone of a rocket and holding on for dear life.
DARPA's a place where if you don't invent the internet, you only get a B.
The DARPA program manager quite literally invents tomorrow.
We are thinking about innovation unconstrained.
Where can we go?
Predict what is emerging as threats.
We're looking for the applications that seem impossible.
That passion will be saving lives 5, 10, 15 years from now.
Coming to work every day and being humbled by that.
The innovation and collaboration, it's a team effort.
We're not builders of the ultimate technology.
It's the engineers and scientists at the companies and universities that we fund that ultimately are going to bend metal and write code and deliver these capabilities to the warfighter.
DARPA is not one person or one place. It's a collection of people that are excited about moving technology forward.
And DARPA Forward is the name of a conference series that we're in the middle of right now. So if any of this has appealed to you, first of all, if you've ever worked on a DARPA program, you are part of DARPA. If you're ever thinking about doing it, think about attending either virtually or in person the DARPA Forward conferences. We have 2 under our belt. Next week I'm heading to Columbus, Ohio, and as you can see, it's a little bit of a brutal travel schedule for us. It's a lot more fun in person, but we have done everything we can to make the virtual experience good as well. And we've put a couple of our folks through, living this virtually, and they say it's actually not bad, which I think is, which is pretty good. But the bottom line is we're trying to give people a little bit of deep immersion into the DARPA experience for a day and a half. So if you've ever wanted to come hang out with DARPA PMs or tell them what they're doing wrong or what you think they should be doing better, I'm just throwing this out there as your opportunity. And with that, end of the shameless DARPA commercial, and I'm happy to take questions.
Very, very cool stuff. Do we have any questions in the audience for Dr. Tompkins? And we do over here.
Thank you so much for the awesome briefing, by the way. So my team has been thoroughly exfoliated by the DoD acquisition process over the past 3 years. How do we close the so-called valley of death with getting things bolted to things in the real world?
Yeah, the valley of death is the infinite question for which there are an infinite number of answers, some of which are useful at any moment in time and the rest are not, right? So I'm gonna lean in on where we're doing a lot of stuff commercially, which I'm guessing is more useful. One of the things we have done is started up this thing called the Embedded Entrepreneurship Initiative. And what we have got are a whole stable of very successful kind of startup company founders, CEOs, that can either be advisors or even can be brought on as more intimate team members with DARPA-funded companies. These can be startups or existing companies to help them figure out what the trajectory for their technology is, whether that is starting a new company and building a business plan so you can get commercial investment, or whether that is finding the best and most useful way to license it. We have had a lot of success on that. I will be frank, a big part of this is the fact that we want, from a DoD perspective, we have to work a lot with US companies, and that means we need all of our technologies to get lots of good US investor money. And US investors are picky. They want like a guaranteed return on investment practically. So what we do is we're working very hard on figuring out what those commercial business models are to help make sure that the companies can go forward. Does that help a little bit? Or was that not what you're asking?
We're on the other side.
Okay.
So we're trying to figure out how to get some of your PM's work inserted into actual units. And we're trying to close that gap. I'm trying to describe, there's this, Crystal City problem where if it's not a program of record, it doesn't exist. How do we solve that half of the equation?
Okay, so multiple paths, and a lot of the things that we are doing, in fact, in some of our communications programs, we have decided to sort of bypass trying to become officially going into a program of record, and we've instead kind of adopted the subversive model where we get whatever relevant pieces of the software that we need into every program of record out there so that they wake up one day and suddenly realize they're addicted. Another thing that we have tried is actually taking our DARPA program managers, and when they leave, if they aren't already committed to a specific job, we're looking at ways where we can actually place them in the gaining organization so that they can then become the champion in the kind of the pull. We have done that, I think, quite successfully with the Air Force, and I'm having conversations with, kind of at the chief of staff level with each of the other services, I think that if DARPA is willing to pay those people salaries, which we are, and if we can get congressional permission, then we can start putting our own advocacy in. Is that kind of thing that would help if we could make that work for you?
Absolutely. Navy, sooner, faster, please, if at all possible. Thank you so much.
Okay.
Hi, thanks for the great keynote. I was very happy to see like open source pop up on some of the programs, and I was like curious if you have like a consistent theme when that makes sense to call it out. Because I mean, you could say like for some, if you want to bootstrap industries, you would probably not want to go open source because you want companies to retain IP. In other cases, you might have like, I don't know, security concerns. I don't know. I was wondering if you had like a theme or like a common reason to say this is a program where open source makes sense and where it doesn't.
So the answer is no, we don't. Although I would think that most of our program managers, when they're designing this, they're going to go through a pretty similar logic chain, and they're going to try to think about what is the best long-term chance of success for a certain technology to thrive. And the general assumption is the more closed it is, the more long-term resources have to be set aside to keep something updated, and and sort of healthy and relevant. So that's not a great model for the DoD. So as you can imagine, if we possibly can, leaning to an open source community, or even kind of maybe a closed open source community, but one where you have a lot of flexibility, is much, much better for not just terms of cost, but also for the chance that software will continue to update and maybe do things we had never imagined in the beginning. So, but the bottom line is each program manager, as they create their program, they are thinking through those kinds of questions. They're being quizzed and helped by a lot of DARPA experts that will help them get there, but that is something the PM has to care about and believe in and champion themselves.
And I have a question, if I may. At the beginning of your keynote, you mentioned how the launch of Sputnik was less a surprise to the scientists than it was to the politicians, and that was the impetus behind the foundation of ARPA. To what extent today is DARPA isolated from political concerns? Do you get to work, how independently do you get to work from, sort of the everyday congressional battles that we tend to hear about in the news?
So as you can imagine, Congress has oversight of our budget, and we work very closely with both the House and the Senate and with the sort of the armed services relevant committees all the time. We keep them up to date. They are extremely smart people, but primarily the staffers that we work with, but all of the members, whenever we are in sessions with them, we find that they're asking great questions, and they really are kind of, we're lucky in this particular committee. They do a lot of homework, they think a lot about it, and they're very passionate. I did mention that, because we started 60 years ago, we have this great track record of success. That has allowed us basically bipartisan support, and they have worked, I think, tirelessly to make sure that we maintain the freedom and flexibility that allows DARPA to be DARPA. So, for example, if I really wanted to, I could hire a new program manager in about 48 hours. I probably don't want to. I mean, if nothing else, that person might need a chance to catch their breath. But we have that flexibility, whereas in classic parts of the government, and I think Tom has experienced this in this, it can take 9 months. There we go. Yeah, and nobody blinks. They just think, oh yes, that's the normal way of things. Of course, you're going to sit and wait for 9 months while you wait for your job offer, right? So same thing with the fact that we can start our programs without having to ask anyone for permission. We have a lot of these flexibilities built in. So we report to Congress. We're talking with them regularly, but we don't see them trying to interfere, and we have never really seen a political, sort of what you're thinking in terms of political influence pushing us to do our job.
Hi, good morning. My question is, how is the war in Ukraine affecting the investments that you've already made, or making you change investment, or where you place, energy and time and resources?
No, that's a great question. There are a couple of things that are happening. So one, I won't be able to talk about much, but as you can imagine, we went through our entire array of ongoing programs. At any moment in time, we have about 250 of them, by the way. We start like 50 new ones a year. So we looked at everything we had to see if there was anything that was either close to ready or could be accelerated where it could be useful. In any case where the answer is yes, as you can imagine, I'm not going to talk about it. But what we're doing that's a lot more interesting is we can look at the things that we're developing, particularly the really hardcore kind of military capabilities, and say, if the thing that we're doing had been available in February, what kind of a difference would it have made? And it allows us to really kind of test and challenge our own assumptions as to whether we still think the idea is actually relevant and game-changing or not, right? So, I mean, I'm really sad that this is being done at the expense of the Ukrainian people, but it's an incredible sort of way for us to learn lessons and kind of come back and rethink our assumptions. And I will say, in case you didn't know this, it was DARPA that created the Javelin missile. So we have had relevance in the past to which we can actually see the use today. So, yeah.
Any other questions from the audience? Oh, I see one over here.
Hello, I was wondering, is there any particularly interesting programs at DARPA that you could tell us about that you particularly enjoyed working with?
Well, so I have 250 children, and I love them all equally, of course. But you want me to talk about something kind of completely different? We have a lot of really cool things going on in the world of supply chains, not just semiconductor supply chains.
Is there any that you found that was your favorite that captivated you, that you found interesting and might want to share?
Well, I think we're creating food out of we have two programs. One creating food out of thin air, using water and bacteria, and the other one creating food out of garbage, mostly plastic. So the plastic one is a little ahead. They've actually created nutritious food bars, but they won't let me taste them yet because they said that is not what they were optimized for. So they're still working on that. But as you can imagine, I find that particularly interesting for a whole variety of reasons. And then we have another program that is actually trying to extract water from air. Because there's a lot of new advances in chemistry, in sorbent materials. So the idea is that you could extract water even from really arid desert air that could sort of keep military units functioning, or we could use that water to create the food, right? So so that whole combination of things is particularly fascinating to me. My own technical background in DARPA is in positioning, navigation, and timing. So, one thing I find fascinating, not in the results of my program, but at the intersection of communities. So when you think of the communications world and you think of the navigation world, so much of what they're dealing with is exactly the same physics, and yet they're fundamentally different assumptions get them at loggerheads, right? So when you think about all of the concerns right now, I've already forgotten the name of the company because it keeps changing its name. But in terms of giving access to spectrum right next to the GPS bands and the fact that we can overwhelm those, there's I think both sides are making totally legitimate assumptions, but they're making them from their perspective. So a thing that I found perfectly fascinating as a concrete example of where we can go wrong has to do with when we were working on a program to try to navigate in deep multipath situations. And so we were using modeling and simulation software from the communications world and could not figure out why none of it matched reality. It took us weeks to realize that the developers were rounding off the speed of light to what was perfectly reasonable in a communications world, but we needed about 9 more decimal places for us to function. And that simple error, which nobody thought to ask about because both sides simply assumed that was the only way it could ever be done, caused us, in the end, almost like months of time wasted. So I throw that one out as particularly fascinating because I often come back to that when I'm looking at communities that are trying to cross over each other and they can't seem to get past these barriers. Sometimes there's these really interesting, very obvious in retrospect, but totally non-obvious problems that exist. So for fun.
Hi, I'm very interested in DARPA's radio frequency machine learning systems program.
Yeah.
And I've reached out and tried to get the data set that backs up a lot of that research with the program manager, John Davies. And even though I work for a defense contractor, I'm unable to get that data set unless I have a government sponsor. So I would ask, is there any way that DARPA can maybe create data sets for RF that could be released to, if not the general public, at least the defense industry in general?
The answer is probably. Let me just make sure I write this down coherently. Do you have active government work of any sort right now? Yeah.
I needed a specific government sponsor to get an MOU to get this kind of data. And I know it requires a non-disclosure agreement. And I understand, all of that, but it would be really great if there were something like, and this sort of goes back to what Luke Bogner was talking about the other day, we need a little bit more data to help machine learning systems in something like ImageNet, but for RF would be a great way to start that process off.
Yeah, like those the large language model data sets and things like that. Sure. Okay. No, it's a great point. I've noted it down and I'll try to figure it out. Who would I come back to if we have an answer? We just advertise it publicly?
I know that there is a lot of public research that's been out. Northeastern has used those data sets and published the research, as has Expedition Technology. If it gets published on Archive or IEEE, we'll see that research and pick up on it and follow those links.
If you can't, give me your name at the end too. My guess is that the earlier solution is probably not going to be something we would make totally public, but we could. I can't imagine why we couldn't make it available to folks who are working on existing government contracts. It seems like that.
It should be a low bar.
Yeah. Yeah.
Thank you.
Okay. Getting a workout this morning.
Hello again. So I'm from Germany, and we don't have like a exact equivalent of DARPA in Germany. But not only that, but just as a foreigner, it seems that DARPA is incredibly successful and popular. Like the DOJ is in the news all the time, and it's not always good news. But it seems like DARPA is always something interesting, and I don't know, maybe that's a biased view from outside. But what's your secret? Can you give advice to other people running organizations like that? To what do you have to do to run an inspirational quote to what do you have to do to run an organization like DARPA successfully?
Well, I will say that the UK is in the middle of creating their own. The Australians are trying to figure out how to find budget to create one of their own. Japan actually kind of has. A couple of other countries have been very interested. So it is fascinating to everybody. I think the secret sauce, the most important part, is that all of the technical people have to leave, right? So there are a lot of things. The fact that we have a lot of this freedom, we have congressional support, all of those things matter. But if you really want to be high risk focused, then right at the point that you get comfortable in an organization is when you should leave, because comfort tends to counteract your risk tolerance, right? So, one of the jokes is that the two things that stop you from wanting to take risks are failure and success, right? So failure is obvious. People tend to get real timid, but success is just as insidious, because the idea is that the next big idea might obviate what you did before. And so people have a really hard time with the fact that they might have to give up something that is stable and successful and that they made their name on and they're really proud of with the next big thing. So there are a few human beings, I think Steve Jobs comes to mind, who are sort of intrinsically able to kind of trash their past in order to create the next thing, but most of us aren't wired that way. So the organization has to be. So this fact that, right around the 4 or 5 year mark, we leave, and that includes me and it includes all of the technical people, I think is one of the really important secrets. but it helps to have a generous budget and the flexibility to make decisions quickly, of course.
All right, I think we've got time for one more question, and then we'll move into the break.
So I had a question with how quickly some technologies advance. So a lot of people are looking at quantum for encryption. If something like that becomes an alternative to kind of past methods, does DARPA kind of get rid of all of their older encryption projects, or do they kind of see them to fruition to see if there's maybe a change?
So if that were to happen, and I'm not actually planning on it in the next coming months, it would be a case-by-case basis, right? You'd have to look at what an encryption program was created for and whether or not it was relevant for the class of problems that one had. But we have actually two programs right now really trying to look at this question of quantum computing and whether or not there's a there. And and the jury is out, but when we talk to physicists, it's really almost like 50-50. Those that are absolutely convinced that quantum computing is going to change everything, and those that think that it will result in basically nothing. And even with Shor's algorithm, kind of the one algorithm for which we have at least theoretical proof that it will be useful, we have not yet been able to demonstrate it at kind of utility scale, where you sort of, effectively you get more out of it than you put in. And so we have a program called Quantum Benchmarking, which is trying to help us understand like what we would really be testing for and looking for in the quantum computing domain, and how we would then understand whether or not we were moving forward. And then we have one focused on utility scale quantum computing, which is really trying to tap into all the commercial investments that are out there to figure out if there is a vector of strategic surprise that we just don't know about. But to everything that is public and everything that we have knowledge of, it hasn't been demonstrated yet. So.
All right, and with that, thank you very much, Dr. Tompkins. It was incredible, very interesting keynote. Thank you very much. And I think now we'll do a break. Is that right? Yeah, I'm getting thumbs up. So we'll do our morning break at this point.
Yeah. Yeah, and it doesn't hold this way.
Ladies and gentlemen, our presentation will resume in 1 minute. Like that? Good go. All right, we now have our fearless leader, Derek Cazell, to give a GNU Radio project update. So take it away.
Hello, my name's Derek Cozell. I'm president of the GNU Radio project, and I'll be giving an update on what's happened in the last year and some thoughts on what's coming up ahead. Of course, it would be great for me to be able to give this in person. However, there was some paperwork that was delayed due to changes in the UK government, and it simply isn't logistically possible for me to be there. Believe me, I wish it were. So taking a look at what we have ahead. I wanted to start with an overview of what is the GNU Radio project, because we have a lot of attendees coming who are new names, as far as I can tell. You may be very experienced in the GNU Radio project, but we also hear that there are some people who may use the code, but not be familiar with the overall scope. So to quickly go through it, obviously there is the code base, the core of GNU Radio, its main blocks, runtime, scheduler, GNU Radio Companion as the user interface, all are what I refer to as the core. The sub-projects, Volk, allowing us SIMD accelerated DSP processing, and SIGMF, our new extension, well, not so new now, a couple of years old, and maturing nicely to be able to store signals with associated metadata in a way that's very compatible both with GNU Radio and with a large number of tools and toolkits coming in the wider ecosystem. We have dozens of supporting projects and pieces of infrastructure. That's our website, all of the infrastructure that this conference has been running on. Lots of bits and pieces that sit in the background, not so obvious, but which build up to enable the development and use of the core, GNU Radio, Volk, SIGMF, all of these very obvious front of house features. Then we have all of the active contributors. The code base doesn't just happen, neither do all of these pieces of infrastructure supporting it. The community that's been built around GNU Radio over its 20-year history is really quite impressive, and it's something that we'll come back to again and again through this talk. Obviously, take a look left and right, and you can see some of those people in the room with you, or you may be one of them yourself. Then we have the broader ecosystem of out-of-tree modules. We have applications such as GQRX and others which use GNU Radio underneath its core. Take a look out for the Fisher talk later on during this week. All of the interfaces that allow data to flow in and out of GNU Radio to interface with other tools, other frameworks, and your own applications. All of those aren't developed by the GNU Radio project directly, as far as, it doesn't live in the GNU Radio GitHub space. However, to say that those aren't part of the broader project would be demeaning to those as projects, devaluing, and really not recognizing a tremendous resource that is part of the reason why people use GNU Radio. There are other frameworks, there are other tools, and yet this is something that has a tremendously broad install base, a huge amount of code and time and effort that has gone into making it actually usable and useful rather than simply shiny. This conference, GNU Radio Conference, is now in its, I believe, 11th year, if I've got that correct, and has been evolving and changing to meet the needs of the community and of the project over time. You'll see this year is slightly different to last year, and we're definitely already thinking of things for next year. We have the European GNU Radio Days and other events that occur around the world and offer opportunities for people to get together and talk about signal processing, talk about wireless communications, talk about the different tools and techniques that go into GNU Radio and other software-defined radio applications. And then, of course, there's you. You may have already seen yourself in one of the lists up above, but you're sitting here in this room as part of this conference, or you're attending online, as clearly am I, and the GNU Radio project without the people would simply vanish into the ether in not that long of a time. It's something that has become increasingly clear over the years is that simply a code base is not a particularly useful thing. It has to be the whole package, and that's something that GNU Radio has done tremendously well at. Something that I always love to do, and I always loved it when Ben Hilburn was president and giving these talks, is to take a brief look at some of the things that have been done over the last year. And obviously, these are the ones that are publicly posted up on Facebook. This is the tip of the iceberg, and many of you will have your own applications that aren't making it onto these slides for various reasons, but which are no less valuable. We have a book published in Spain and covering an introduction to SDR using GNU Radio. Whoever the author is here, Miguel, I really hope that they're enjoying GNU Radio. Clearly they did enough to publish a book. Victor Kai was a speaker at GNU Radio conference last year, I believe, or a couple of years ago, and has gone on as a high school student and has gone on to use their GNU Radio experience to continue on to a large competition. We have, posts about using GNU Radio in the cloud, tying it up with Azure. There are some Microsoft folks in attendance. Be sure to catch them if you want to chat about that. But just posting these online demos, it's fantastic, and it gets a tremendous amount of interest in the project. Fisher, as I said, will be having a talk later on this week, a reverse engineering and signals analysis toolkit. Obviously, there are other tools that do this. However, it's great to see one that's built using GNU Radio and can make use of the entire hardware infrastructure, hardware ecosystem of device support that we have, and also making use of a lot of the protocol extensions and protocol development that has been done that allows this tool to be extended and built upon these different pieces. As I said, events, Electromagnetic Field was an event held here in the United Kingdom. It's largely a social event, a camping trip. And yet here we have GNU Radio being introduced to a broader audience of hobbyists and enthusiasts and likely professionals, but not with that particular hat on during the day. And then a master's thesis. I could have filled this entire slide with academic papers and theses, PhD theses, published actually on GNU Radio, where GNU Radio is not simply a tool being used in it, but the actual topic under study, or the core enabling technology, where you can read every paragraph, and every paragraph is dealing with some interface to GNU Radio, or interoperating with GNU Radio. And so congratulations to Andra Maria Elias from ETH Zurich on completing their master's. Here's somebody to try and snap up if you're looking to hire people. Although I've taken a look and sadly already employed as per LinkedIn, but this is building up the community and the next generation of wireless developers, and this thesis is actually a really interesting one, and I hope that we can get Andra Maria in to give a talk to the architecture group, which I'll be talking about in a moment. I'm looking at the clock and knowing that I need to proceed on with this. So FOSDEM runs every year. It's in Brussels the first weekend of February. We've already seen the call for participation published for next year's event. Be sure to add that to your calendars. And here's just a quick overview of some of the talks that were there last year. We were still running virtually, and so it was a smaller event. But you look at this, and we have FPGA acceleration from within GNU Radio, interfacing with Raspberry Pi GPIOs with a variety of out-of-tree modules. adding OFDM radar to GNU Radio, and just a whole bunch of other pieces here. This isn't a GNU Radio exclusive event in any ways for FOSDEM, but GNU Radio definitely shows its integration into the broader community and its utility as an accessible tool, given how often it crops up in this conference track. I did also want to mention the Software Defined Radio Academy and EU GNU Radio Days, two other recurring events. Their websites weren't so easy to screen grab, but they ran again with an in-person event, and there's some great workshops attached to that event. So again, that's a European centric event, but well worth catching all the recorded talks on YouTube if you're not able to attend in person. So that's taking a look broadly at the community. And the community, I think, really is GNU Radio's strength. So why is there a president? Why am I here? Largely, I think that the government structure that we have, that I'll describe briefly here, is one that has emerged out of necessity and out of utility in terms of having a core group of people who can speak authoritatively about the direction of the project, and to be that interface between what is a large, amorphous, and highly varying open source community of diverse people and projects and interests, to be that point of contact with single organizations, single people, and to be able to tie those as a bridge. So our governance structure is that we're an unincorporated association. You can check out on our GitHub repository of all things, our governance repository, which has our articles of association, which covers voting and other logistics. It's how we can act as stewards of the project, and something that's emerged. We talked about governance in past years, but this is really an appropriate level piece for the project. We have a whole range of volunteers. Everyone involved in the governance is a volunteer. We haven't been paying out to anybody. We need to represent that whole broad user base as well as possible, and to be responsible so that we have documented rules and pathways to joining the leadership team, how to hold the leadership accountable should anyone in the room or on the stream or anywhere in the project find issue or fault with the leadership. There are pathways for providing that feedback and actually removing members as needed. Hopefully that never happens. It hasn't been necessary, but we'll see. It's better to have it than not. We also publish annual reports about the activities of the board of directors and of the General Assembly as a whole. It's also flexible, and I'll talk more about how we make that happen in the next couple slides and how you can get involved. But it's really all about just enabling and empowering people who are already involved in the project or were already contributing to be able to act in a fashion greater than they would as individuals. So looking at the General Assembly, this is our core steering group, and I certainly hope that I have everyone. So we have Andre Rode, Bastian Blössel, Ben Hilburn, the past president, myself as current president for one more year and then re-election, Jacob Gilbert, Jeff Long, Johannes Demmel, Mark Lichtman, Marcus Muller, Martin Braun, apologies Martin, Nate Temple, Philip Ballister, and Samantha Plaslow. Several of these people are in the room with you right now. Be sure to seek them out, or please wave. And they are our point of contacts. If you want to talk to somebody about the project, find somebody on this list or the email address that you'll see on the next slide, and get in touch. We can act as the clearinghouse to link you with other people in the community as best fits, or to help move forward whatever you would like. In the end, you as a user and as a contributor are the project, and it is the job of the General Assembly to serve and enable anything that is possible and reasonable and feasible to happen as smoothly as possible. So what we have is a structure of teams, and this has been informally true for quite some time. people gathered into chat rooms and coordinated their actions under these different topical areas. A lot of that was ad hoc at previous GNU Radio conferences. We've had birds of a feather and breakout sessions. We do have breakout sessions later today. And what we've done is just encapsulated that under a couple of names and been able to attach leads to them. So head to the GNURadio.org website and you can see who the current leads are. And we'd like to build up the membership lists of those teams now that they're a real entity. So we have the architecture team leading the development and planning of the future technical direction of GNU Radio. We have GRCon, the planning committee that has made this event happen. Particular thanks right now, please, for Samantha, Josh, Mark, who have been so heavily involved in making this event happen. We've had Barry, who is in attendance, as well as Steve Croft, who will show up on a slide a little bit later, stepping in on many of the weekly planning meetings, and without a much broader group of people as well filling in individual roles, it simply wouldn't be possible to put on this event. So, from me. The infrastructure team, Andre pretty much solely holds up the IT infrastructure for GNU Radio. And that's everything from the Pretix website that you registered your tickets on to Indico, the open source event platform that we're running this event on, and we did the call for participation, the schedule, etc. That extends out to our main website, the virtual machines hosting that. Really, the infrastructure team keeps the lights on. GNU Radio Companion, Hakon is in the room and has been leading the development of GNU Radio Companion purely out of a personal project for some time, and it's great to be able to recognize the amount of skill and time that he's been putting in there. And we've got some great news later that should enable that to move forward at a much faster and ambitious pace. Signal metadata format, Volk, the SIMD acceleration library that I mentioned earlier. Many thanks to Johannes and Michael for owning that and moving it forwards. Documentation, and finally the board, which is currently myself, Mark, and Martin, as mentioned in the last slide. Please, if you have an interest in any of these areas, questions, comments, interested in getting involved, send an email. These are open and public as seen here, and the project cannot represent your interests, your needs, your concerns, unless they are voiced. And hopefully this is going to provide an easier path for general members of the community to most quickly find the right person to speak with. When in doubt, feel free to email me. My email will be on the last slide, the board, and we will clearinghouse you to the right team or jump into chat. But here's some points of contact for you. In terms of getting involved, there is the chat. Apologies, dry mouth. There's the chat, chat.gnuradio.org. Hopefully, if you're here at the conference or attending online, you've already joined. But I got the statistics yesterday for our first day, and no, you haven't. So please do. You can either join directly through our website, or you can join with any Matrix account. The main room for this is #grcon22 on the GNU Radio home server. Join the mailing list. Discuss-GNU Radio. There's a link from our wiki, wiki.gnuradio.org, to find that. Great for longer form questions and more in-depth things that need more files and stuff attached to it. But the chat's great for quick responsiveness and general hangout. File issues. Go onto our GitHub. Report issues. They can't be fixed unless somebody knows about them. Now, we'll talk later about why there's no guarantees that things will be fixed and that there's no set time to respond, but this is really something that is quite important. If you wish to further the project, please do review issues, add details, go onto an issue and try and recreate the issue in the latest code base. We have a lot of open ones that probably aren't accurate. They've probably been addressed. So that's a hugely valuable contribution. That's also a great way of learning GNU Radio as a tool. Improve the tutorials. The tutorials live on the wiki. We'll definitely see them in a couple slides as well, but they're open for editing. Give a talk about GNU Radio to your coworkers, your friends, local hackspace, and get the word out there. The more the community grows, and there is, out of inevitability, turnover in the community, people leaving and people joining, the more we can bring people in, the more the project is capable of doing as a whole. Here's a list of the top couple good first issues on GitHub. So if you're sitting at the conference and you're not quite sure what to do with that spare 10% of attention that isn't going to the talk, or you just need a bit of a break, check out one of these. Even if you're a really experienced developer, or perhaps especially if you are, this is a great way of really quickly knocking out something that's going to make life better for everyone here. If you're brand new, dive in anyways. And when you hit a problem, because that's just what coding is, then jump into the chat or find somebody around. Probably the CTF room is a reasonable place to find some people who are hands-on and going to be diving in. Ask questions and you'll get help. The block documentation, head onto the wiki. You can find any of the blocks that are in the GNU Radio core. Just open up one of these pages and you'll see some of them have lots of examples and details, flow graphs, photos, and that's something that you can extend for the ones that are missing that. Or try out the block and go, actually, it doesn't quite work that way, or it does, but that wasn't clear, that was not obvious, and document it. We're going to have some work that will be bringing this documentation on the wiki much more in close contact with the tool. So improvements made here are going to have a big impact later on. So again, this is listing out those resources. Please do jump in. Now, what else is the project? We are also partnered with the SETI Institute. This is something that came about in 2019, and we partnered up with them because as GNU Radio grows, our administrative and logistical needs have grown, and the partner that we were with at the time, the Free Software Foundation, was great. They were doing, we had the great philosophical alignment with them as we are a GNU project. However, they aren't experts in software-defined radio technology. If anything, that's our job within the GNU project. And so the SETI Institute was a really natural partner, as they are massive large-scale users of software-defined radio. They handle bandwidths that you don't find in many other applications. And they're completely open and transparent and interested in public outreach, education, and research, all of which are aspects of the GNU Radio project and of our community. And so there was a fantastic mission alignment there. Also, we had to deal with finances and logistics. An unincorporated association signing on to a contract with the Hilton, not something that's going to happen quite so easily, and no doubt we would miss things if it were simply us as a couple of engineers trying to make this work. And so I have a bunch of shout outs that are inevitably going to be insufficient to people within the SETI Institute who have been involved in supporting the project with their experience and skills in areas that we didn't have ourselves within our volunteer base. So Rebecca McDonald, who I'll have a photo of in a moment, is Director of Communications, and you'll see her at the GNU Radio conference. CEO Bill Diamond has been meeting with me and talking about the long-term vision of where GNU Radio and SETI can work on collaborative projects, and also just offering really some advice on how administratively can an organization grow from a small piece. Now we've set up a leadership structure. What are the next steps? How do we develop beyond that? And so then Steve Bordeaux and Amanda Shenik are part of the SETI Institute development team, and we will almost certainly be leaning on them more heavily in years to come as we try and find new ways of reaching out to more of the GNU Radio community. Ben Hilburn, in some of his previous project talks, has described how really what we see publicly is only 5–10%. Nobody knows the number, but it's very evidently not a large percentage of the GNU Radio users and use cases. And so we need to find new ways of reaching out to a much broader base of users who aren't going to be engaging in the same ways as the existing people who are publicly represented and publicly involved. Debbie Collier is leading up the SETI Institute grants team, and there will definitely be some slides on that in a minute. Shelley Smith, June McGee, handling finances and accounting. We do end up with a lot of traffic, mostly around GNU Radio Conference. There are hundreds and hundreds of you, and that's just a lot of moving pieces and pieces of, well, not paperwork anymore, but line items that we need to get right. We have our taxes to pay, all of that, and they've been a tremendous help with that. Yvonne Nicholas signing contracts. In the end, she's the one who has the experience to make sure that we're getting the right arrangements out of people and organizations that we partner with. And finally, Lee and Jasmine, who have been doing graphics and swag and other artistic support and design support. So if you've bought one of the shirts, you've benefited from some of their work. I am running definitely short on time, so I'm going to really try and hit a pace here. We ran a Hackfest in 2019 with the SETI Institute at the Allen Telescope Array, a 42-dish interferometer in Northern California. It was fantastic. COVID hit. We will be looking to return probably to the ATA, but certainly to a Hackfest partnering with the SETI Institute in the spring or summer of next year. So look forward to announcements on that. Sorry, we don't have a date quite yet. On site with you, Dr. Steve Croft. Check out his talk at 11:30. Rebecca McDonald, Director of Communications. You may have seen her at the registration desk or at the SETI Institute booth. She's got a great perspective on what the entire institute is up to. And Dr. Wael Farah, who is involved in instrument design, DSP authoring, and machine learning at the Allen Telescope Array, and have background at other instruments as well. So be sure to find them, thank them for their support of the GNU Radio project, and get to know them. They've got some great backgrounds that many of us could benefit from, and the project certainly. On to another section that I've inherited from Ben Hilburn and quite like. The lies, damn lies, and statistics section. So here we see a basic plot of contributions over time. This is largely meaningless, except to say that GNU Radio continues to be developed at a great pace. And while I probably should have put a marker on here, I think you can see when Josh Moorman took over as lead maintainer of the main development branch, which is largely what this plot is representing, as we can see a great uptick from 2020 onwards. And so look forward to bright futures. Now, this is a great one. When did you order your ticket? Part of the nightmare of running the GNU Radio conference is not knowing how many people are going to be attending. And actually, if we look at our gray line here, this is a plot of the percentage of orders over time leading up to the day of the event. Over half of you had not registered as of well, less than 20 days ago, so less than 3 weeks ago. Yes, this is fairly representative. Yes, this is the worst year in recent history. And no, we didn't have late registration tickets. I'm not saying that we'll reintroduce them next year, but please don't be surprised if we do, because this is stressful. Yes, we reach a great endpoint, but cash flow is a thing, and food and beverage guarantees and numbers and ordering, all of that logistics is a lot easier if we have some information ahead of time. Now, this plot is normalized, so it's a great statistical demonstration, and it gives us some good information, but I know that there's going to be people out there who actually want to know the base numbers. So if we take a look at this plot, we can see the number of attendees for the last couple years. There's some fudge factors and roundings and errors in here of a couple percent, depending on how you count orders, etc. And significantly, this is only in-person tickets. A plot that I don't have, but will definitely make available later on in chat, is the virtual orders for this year compared to the last couple years. We can see that we had a great progression going from 2018 to 2019, and we don't have the base number, this degree of detail for 2017, 16, etc. But we've basically been marching very nicely up in attendee numbers, which is great to get more people in the room and more discussions happening. COVID hit, ouch, pain. 2020 online, really not representative, so not included in this plot. We had 1,600 online attendees, which is great, but would completely blow out the axis. Looking at last year, I think one of the big takeaways for this is I'm tremendously glad that we ran the event, and that was the sentiment that I heard from people in the room and people online. It was tremendously valuable to run the event and to return to not lose the traction that we had. Obviously, the attendee numbers were much lower, but it was great to have the people that we did have. And as we can see from 2022, it's surging back up to the previous numbers. So 2023, looking forward to a fantastic event. Hopefully with some early registrations, please. One of the other notes here is we can definitely see there's been a large variety in when we've opened up ticket sales. We will be opening up ticket sales a bit earlier than this year, aiming for kind of that February time frame. We'll see when that goes, but there's really nothing holding us up from almost opening it today. More stats. On GNU Radio, we have the number of people who have been cloning. This is a 2-week time span. And so we can see that there were 950 unique clones just from GitHub. Now we also have our cgit at GNUradio.org or .GNUradio.org instance where you can download all of our code is mirrored there. It lives on our own infrastructure there as well. So that's not 100% of the people cloning via Git, but it's probably pretty close. Having looked at the 2019, 2020 numbers, this is significantly higher. It's a 50% increase, I think it was. And so we have a lot more people pulling there. But also, if we take a look at the other plot here, the CondoForge bit, which thanks so much Ryan Bowles for packaging GNU Radio, there's almost 400,000 downloads there. I would love to understand this number a lot better. But I think the big takeaway for me is that our packaging has improved and more people are installing it through apt, thanks Maitland, and through other packaging methods in Access. And so while we're getting more people cloning Git, I view that as probably the developers or people following somewhat older or flexible instructions. The packaging, I think, really represents a bit of a better view into kind of the behind the scenes dark user base where we have a really significant presence. Also, we have a tremendous number of people visiting, 3,500 unique visitors to just the main core code in the last 2 weeks. That's a number which really helps me get up in the morning and stay involved. It's great to see so many people interested. Now, we also get to see where those visitors are coming from. And in the past 2 weeks, a large percentage of our visits to the website have come from Falcon Blog, a Japanese individual's website where they publish an FM stereo receiver with some parameters that I can't understand. But it's fantastic to see, again, the impact that GNU Radio has around the world. So jumping, as I'm conscious of time as well, into funding. GNU Radio has long had a cycle where we would basically year to year have zero income growth. Our expenses met our income, and that is no longer the case, which is great. And that's a trend that's been happening for the past couple years. COVID was very nerve-wracking. We didn't have the same type of income then that we did from the conference, obviously in 2020 or 2021. But we are now at a point where the project actually has some cash in the bank. And by the bank, I mean SETI Institute's accounts. And so this conference isn't done yet, but we do expect it to produce some revenue, some profit. And so we're looking at ways of reinvesting that. I've got a couple notes on next slides, and we're looking for feedback as well. Where would you like to see GNU Radio spend money? So the conference is a huge expense and our vastly biggest source of income up until now. We've also started pulling in some grants. We have methods of donating. This doesn't quite add up to the project having a clear business plan, as it were. We're not a business, we're a nonprofit, and organizationally just not prioritized and structured commercially. But there is a need to be sustainable, to be able to support the efforts that the community's needs require. So looking at grants, we've got NumFocus, ARDC, and the NSF. NumFocus is a nonprofit in the United States. We joined it as an affiliated project in 2021, and in the fall of 2021, we applied for and were approved for a small development grant. This is a system that they run several times a year to do a revamp of the tutorials. Many thanks to Mark Lichtman for leading the writing of that application. He's been our major interface to NumFocus, and he also executed the performance of that grant once issued by hiring Matt Carrick of Wavewalker DSP to run through our tutorials, edit the ones that existed, and end up rewriting a bunch of the ones that were there to be a substantially more useful set of tutorials, going in more detail with better flow, better pedagogical content. How do you actually onboard somebody to a tool? And a lot of that ends up being teaching the plumbing of the tool in a way that's accessible and enjoyable, but getting in the pieces of information that they need when they need it. He also wrote several new tutorials and pages. Please do check this out. wiki.gnuradio.org or tutorials.gnuradio.org. They're a great resource, and we've already heard somebody yesterday comment how even after years of experience using GNU Radio, this is a great resource for them to find and use new features. We also have developer resources for porting from earlier versions to the current. So the idea has come up that GNU Radio should do some of its own small development grants. As I said, we expect to have some money in the bank that we can spend and invest in the project. We won't be spending $100,000 on some huge effort based off of what we currently have. That's not the sort of income that we generate. But we can absolutely do a series of $5,000 grants, a $10,000 if that was something that really made sense. And so there's a wiki page called Grant Ideas. Also, please email ideas to any of the teams that you think would be able to spend money effectively. If you have ideas, we want to hear them. If you have needs that you think are well matched with this sort of structure, definitely let us know. I've included the NumFocus steps here. This is not something that we're committed to adopting. It's not something that I've honestly spoken with a lot of people about, but in thinking more about this talk, this was something that came up, and I think that we could embrace some of the process here, because any decisions that the leadership makes, any decisions that the group of stewards makes, needs to be accountable and responsive to the community. So this seems like a nice place to start the conversation. ARDC, also present in the room with us now. Please raise your hand. I believe it's Dan who's attending. ARDC is a nonprofit in the United States as well, whose mission it is to support digital communications, science, technology, and education experimentation. And so we applied for a fairly large grant for them, and I'm really thrilled to say that we received this. So it was awarded in March of 2022. It is $260,000. That is the total number. There's some overhead involved in there. So the working amount is somewhat less than that. But it's to fund a set of core improvements to GNU Radio, which I'll quickly run through on the next slides, and you can find more detail online. We had a 6-month setup period, and we're basically coming out of that. So we're looking to hire on people to execute this grant over the next year and a half. So next year's GNU Radio conference should have at least one talk, if not more, covering the execution of this grant. I'm tremendously excited about this. This is game-changing for GNU Radio in the past decade. Out of this, I'm going to quickly gloss over this. The slides will be available online. We have, or hit pause, of course, if you're on the recording. Installing GNU Radio's been a constant pain point. As much as we get new packaging, there's still a lot that isn't covered, and a lot of the packaging could be easier if GNU Radio itself was structured slightly differently. We do a good job, not a great job. And out-of-tree modules are largely unpackaged. As much as Ryan and Maitland have been working, there's still dozens and dozens of out-of-tree modules that are not simple to install, and particularly on Windows. There've been some community efforts. I looked, and I think a lot of those have now shut down. It's a volunteer-based thing, so it needs improvement. We're going to fund that. If you have experience developing installers on Windows, please reach out. The email address is on a slide or two from now, jobs@gnuradio.org. Same for Mac OS. We want a binary installer for both of these. We want binary installers for out-of-tree modules. We want continuous integration and testing, etc. And we want that for out-of-tree modules as well. Documentation. Taking the usage manual that we have, the block docs, the tutorials, and making offline and portable versions of those. Going through example flow graphs and validating that they work, improving them, documenting them. In another round of improving tutorials. There's definitely still ground to do there. Obviously, we had a great experience with Matt Carrick. We are going to be looking to hire on more people as contractors to perform these pieces of work. Software maintenance, going through all of our issues and just cleaning them up. You know, the triage system is really essential here. We need to cover this. Continuous integration testing, that's really largely been done since by the community since we started writing this grant, but there's absolutely room to improve and add more tests. And so that's definitely an item that's still necessary. And our integration testing can definitely be extended onto these other platforms. We are now building on them, but there's a difference between building and actually exercising the tool. And so we want to improve that. GNU Radio Companion. It's been a great tool for many years. It will remain a great tool, but it doesn't have a preferences window. There's a lot of the documentation that isn't easily accessible. You can't manage and view the out-of-tree modules that are installed, what version, paths, stuff like that. The examples are largely unknown to many users, so adding an example menu. None of these are groundbreaking changes. But added up all together, I really think it's going to change the new user experience and just all of our quality of life. I don't want the pain and effort that there is right now to do a lot of these things to continue. We all deserve better. And because of ARDC, we're all going to get better. So look forward to that coming up. And if you can think of people who would be able to perform this work, please get in touch. There was a tail end of the grant, which covers project management. This is going to be a new thing for the project. We are actually going to be funding a member of the leadership team to be coordinating this grant as a paid activity. The salary is not competitive with, you know, a top tier job, but it's a heck of a thing for what has been a volunteer role up until now. We're also getting professional services from the SETI Institute. So we're hiring. Email us, jobs@gnuradio.org. Finally, I want to talk briefly, as I know I'm at the end of my time, about shifting gears. For folks who have driven manual cars, stick shift, you know that feeling of when you are pushing your engine as hard as you can go and everything's heating up, and you just know that you're going to wear things out if you continue at the pace. GNU Radio has had waves of development, waves of in its life cycle of where the effort is going and where the greatest need is. For a long time, it was simply building the tool. Then the tool became intensely usable and a great resource. And I started coming on the scene around when 3.7 was the main version. And we got a great number of years where people were building applications and out-of-tree modules, and a lot of the energy was going into the broader ecosystem. Now we see that there's a great need to improve the core, and check out Josh Moorman's talk tomorrow on technically where we're going in 4.0. We need to deliver that work. We need heterogeneous compute. We need distributed compute. We need the ability to in a more nuanced fashion, express how the work should be performed and where. All of these things are on the roadmap and are being developed. But in order to make the most use of that, the organization is being put under, the volunteer group is being put under a lot of pressure to make this function. So we need to shift gears. We need to move to the next level and change what the GNU Radio project looks like in some ways. And I wanted to end the talk really on this, flashing it up. This is a grant run by the National Science Foundation, the Pathways to Enable Open Source Ecosystems. This honestly is a huge stretch for us. The demands by the NSF on what constitutes a grant application is much higher than NumFocus or ARDC were expecting. The SETI Institute has a great background in applying for NSF grants and receiving them. The coordination and management and reporting, all of those are a higher standard. But this grant is custom built for GNU Radio. It's all about taking an existing framework, which we absolutely have, an existing ecosystem, which we have, but we know that there's a lot of pain points in. We know that the out-of-tree modules go out of date. Authors leave. We have no handover structure for that. We know that the project as a whole receives a lot of offers of collaborations that we're unable to be responsive to because we're a purely volunteer group and we just don't have the number of people, the number of hours, and the office support, the administrative capacity to interface with a fast-moving company or organization that's trying to develop some cutting-edge feature. And that's exactly what Posse is designed to facilitate the jump, facilitate this shifting of gears. So we're planning on applying to this. The timeline's pretty short, and we'll see if we make it. I really hope so. And that's going to be a big thing for this next month, is making sure that we do. How can you support? Get involved. Advertise that you use GNU Radio. Please let us know that you use GNU Radio and let us recognize that. We're going to be creating both slides and support documentation and some recognition on our website of companies, organizations, and individuals using GNU Radio. So get in contact if you're willing for us to use your logo and name and say that you're a user of GNU Radio. Write a letter of support. A lot of these large funding organizations need to see that the project has impact and some details about it. We can keep these letters of support confidential because particularly one of the things that's expected, particularly in Europe and the United Kingdom, but also in the United States as well, is the actual economic impact. And we don't need, the whole financial records, but what do you think GNU Radio is worth to your organization? We're not expecting money from you, but we could really use some of your information and support so that we can go to these other organizations and get that money from them, get these grants. Publish a white paper. Again, that's visibility and evidence for us to support what we're doing. Join a team. Contribute your experience. All of these make a huge impact to the project. So if any of those sound like things that you can do, get in contact with one of the teams if you want to join them. Join the chat, etc. We all hang out there. We're there quite regularly and very accessible. You can also contact me directly, dkozel@gnuradio.org. I'm on Matrix, our main chat system, and I'm on Twitter, if you're more of an open and casual person or would like, as an organization, to start highlighting things, we'd love to promote the projects that you're doing and your use of GNU Radio through our channels as well. So thanks very much, and have a great rest of the conference. I hope that I can be there in person next year and see many of you in person. Bye.
All right. Are there any? Martin has said that he is willing to sort of act as a proxy and answer any questions that may ordinarily have gone to Derek were he here. Are there any questions in the audience surrounding GNU Radio, the organization, updates? Ah, there's one in the back.
Derek, thanks a lot for your presentation. This is Wael from the SETI Institute. It's great that you're thinking about grants to move forward with the GNU Radio project. I was just wondering, what's on the big scale of things, is GNU Radio following an academic model or some form of a startup? What's your general thoughts on that?
So, honest answer is we're not quite sure. So we're lucky to be tied into the SETI Institute. That gives us some flexibility. So we, bring in money into this. We can park it at the SETI Institute, and we can take it out and then pay people, contract stuff out, or whatever. So our mostly volunteer-run organization will remain the way it is, and that's very important. So we set like a very Derek talked about the governance structure. It's actually, like pretty well defined at this point. We have like, what are they called? Articles of association, and like guidelines, rules, stuff like that. We explain how you can become a member of the General Assembly, which is the main governing body, etc. And we don't have millions and millions of dollars, so these will remain voluntary positions. Or like in my case, like there are entities like industry entities, could be universities or whatever, who say, okay, like we are willing for our employees to spend a certain amount of time on the project, and then we will still try and raise money to be able to either pay people directly or to contract out tasks. And we're gonna have to try a little bit how we want to evolve. It's very complex though, because I don't want to go into too much detail, but for example, with GNU Radio 4.0, there's like many different directions that we can take it, and it sort of depends on like the interest. So it's highly it's a highly not volatile but iterative and sort of feedback based approach. So we don't have like an idea for a product like a startup that we want to sort of push out. So we want to our goal is to provide free open source SDR, like the thing that's free and open source and SDR to the community, people like you who are doing research, but also people like in the industry who might just want to have a tool for some RF interaction capabilities. So and it changes on a daily basis. So I can't give you a better answer than my rambling.
Real quick, just wanted to, because Derek forgot, and I'm going to call him out on that. We haven't been able to do this for a while, but for GRCon 23, we actually are teaming with Arizona State University, ASU, and we'll be hosting that in the Phoenix area. So just wanted to make sure that, oh, yes, one change that's happening due to scheduling is we've been running the conference kind of in the later September range. For next year, it'll actually be during Labor Day week. So we're trying that out. And as always, we do look for input from the community, right? So we look forward to doing this again next year. And I will let you go back to the questions.
Actually, first people are bringing in their plates, so I think we'll just call it. I'm sorry. Yeah, I think we'll leave it at that. You can obviously ask me questions. You can also ask Derek questions on chat. Sorry. Yeah. Yeah. So before we head into lunch, though, I have one thing. Whatever it is, you guys gotta wait. Sorry. Before we head into lunch, I do have one announcement to make. So we had a case of confirmed COVID yesterday. One of the participants tested positive, and has already self-isolated, etc. So we've taken all the possible precautions. Room this size, this was bound to happen. I'm still not happy to have to make that announcement right now. We have masks at the front desk. We have PRL everywhere. Please wash your hands. Don't touch your face. Yada. You've been through the same pandemic as I have, you know the drill. Yeah. But for the sake of transparency, we wanted to let you know, like for the, we had a known case of a participant yesterday here who has now tested positive. So, like how do I go from here to enjoy your lunch and have a great rest of the day? I don't know. I'm just gonna leave it at that. Bon appetit and stay safe.
Real quick, if you did not get chicken and you were desperately looking for it, there is some out now, and also some additional cake. Apologies. I know there were some people that were waiting. Sorry about that.
Okay, everyone, we're gonna very soon start with our afternoon talk sessions. So if you could, like people in this room, you know, settle down. You can finish chewing the lunch. That's fine. And maybe, you know, the expo booth hall, the expo booth. Yeah. All right. And real quick, so there's like 2 tutorials going on right now. So I mentioned to a couple of people that we weren't sure if you could do the RF tutorial. So that's been cleared up. It's happening. So if you want to learn about RF you go to the room that's like opposite from the registration desk. And there's also an introduction to, that's right now, right? The introduction to GNU Radio and GSC, that's sort of more beginner focused. I can't remember which room. South America. So not actually in South America. It's like one of the rooms. It's on the map. Yeah. So those 2 things are happening right now. Okay. And other than that, are you ready to go? Okay, then we'll kick it off to our first speaker, Isabel and Jacob from ASU. Vital sign sensing in GNU Radio. Oh, Isabella. I'm sorry, Isabella. Yeah. Take it away.
All right, can you hear me? Okay. Hello, everyone. My name is Bella, and I'm a PhD student at Arizona State University, and I'm here today with my lab mate, Jacob, to tell you guys a project that we put together where we built a radar system using a software-defined radio and GNU radio that's capable of sensing heart and respiratory rate. So Jacob and I, like I said, we're from Arizona State, and we're part of WSCA Labs under Dr. Daniel Bliss. So these are the topics I'm going to go over today. But before I get into too much technical detail of the actual project, I'm going to give you guys a little bit of a background on the physiology of your lungs and your heart, which is a little bit outside the realm of what's normally talked about at this conference, but thought it might be good to build up a little bit of a background. So when we breathe, we're bringing oxygen-rich air from the environment into our body and expelling the carbon dioxide out of our body. And the way that we do this is by contracting our diaphragm in a way that expands, that pulls your lungs down and causes your chest wall to expand. This creates a negative pressure inside of your lungs. Because of that negative pressure, the oxygen from the environment is able to flow into your body. And then when you want to expel the carbon dioxide out of your body, you allow your diaphragm to relax, and this causes the carbon dioxide to expel back into the environment. And a typical breathing rate for a healthy adult is 12 to 20 beats per minute, but this can vary significantly depending on if you're exercising or relaxing, and then also person to person. But significantly higher or lower rates can signify different disease states, and for this reason it's an interesting metric to keep track of. So now switching over to the heart. So your heart is a muscle, and it contracts for the purpose of circulating oxygen-rich blood to your tissues and then bringing the oxygen-poor blood back to your lungs. And the way that it acts in this pump is by the muscles actually physically constricting. And so this is a movement. So when you hear about your heartbeat, what is being counted here is that contraction of your heart muscle. And a typical resting heart rate is about 60 to 100 beats per minute in a healthy adult. But this also varies significantly depending on if you're exercising or relaxing, and then also person to person and over time. But significant changes in your heart rate over time or resting heart rates a lot higher or lower than this range can also indicate different diseases. So for that reason, this is also a vital sign that's often kept track of. So traditionally, your respiratory rate is monitored just with like a physical count. So if someone's just gonna watch a patient or a subject and stand and look at their chest and watch how many times the chest moves forward and backwards. And this is a intermittent measurement that's completely subject to human error also. And because the person has to actually like take part in it at all times, it's only tracked, it's very rarely tracked, and often in a clinical environment they don't keep track of it at all. But it is a meaningful vital sign, so there's motivation for a better way to keep track of this. And then in parallel to that, the heart rate is typically monitored using an electrocardiogram or an ECG, which this is a measurement, or this is a measurement that measures the electrical conductivity of your heart. So when those muscles in your heart are contracting, there's electrical impulses that are firing in a way that you can track what's going on. And the way that this is tracked is by attaching electrodes directly onto a person's skin. But there are drawbacks to this in that it's kind of uncomfortable, and also like if you're in a clinical environment, it's hard to interact with a patient that's wearing these, and you kind of need to be in a hospital or something in order to have this measurement taken. So an alternative way that the heart rate's often measured is with the PPG, which this is an optical measurement. So you're actually shooting some kind of optical wavelength towards the skin, and it's measuring the absorbance of that light that's sent at your skin. And the absorbance differs depending on how much blood volume is in your extremities. So when your heart beats, blood rushes into your extremities. So there's more blood in your fingers and toes right after it beats, and that's what that measurement's measuring. So if you've ever worn a smartwatch or a pulse oximeter, that sensor in the middle there, that's the measurement that this is taking. But both of these are contact-based, or all of these are contact-based or intermittent. So for kind of obvious reasons, there's definite motivation to be able to monitor heart and respiratory rate without contact in a continuous fashion. So for that reason, for many years now, people have started looking into using radar to monitor your vital signs. So the idea behind this is that you can transmit a radio signal towards a subject, and their chest wall moves in a way that modulates the transmitted signal, and that modulated signal at the receiver contains the information of your heart and your respiratory rate. So I'll go into that a little bit more on the next slide. So if you look at the guy here on the screen, you'll see that there's that red wave coming through the air, and then there's an orange wave coming through the air. So picture that the red wave going first, and at that point in time, the subject's chest is recoiled, and then at a later point in time, that orange wave is what's being reflected off the chest, and the chest is expanded further. And so because that distance has changed, the location that the two waves hit on the receiver, or that triangle in the middle of the screen there, has changed. So according to Doppler theory, if you reflect a tone at an oscillating target, in our case the chest, it's going to return in time with time-varying phase that's proportional to the displacement of the object. So if you imagine now that that receiver that's in the middle of the screen, you flipped and now you're looking at the front phase, that tip of the phaser there, so the edge of the arrow, is going to oscillate with time depending on how far away the chest is. So for this reason, you're able to track the way that the chest wall is moving, and that's going to contain the information of your heart and respiratory rate. So over the last several years, a lot of research has gone into this area using many different approaches. So what I explained on the previous slide was unmodulated continuous wave radar, but there's also a lot of other types of radar that have been used for this, including frequency modulated and ultra-wideband pulsed radars. And then there's also a lot of interesting research right now that's going on using phased arrays and MIMO configurations in order to monitor multiple subjects at one time. And then in combination with this, the post-processing techniques that you use to extract the heart and respiratory rate from the received signal vary a lot. And most of the research to date has been done using specific hard-coded radar sensors, like these pictures that you see on the your right side of the screen. And in the WSCA labs at Arizona State, we've been doing a lot of research in this area, and that's how I kind of got involved with this lab, is because my research interest is in biomedical signal processing. And in addition to heartbeat, we've also used radar to monitor other signals of the heart, including your RR interval and then the acoustic signatures of the heart, which these are correlated with even smaller movements, so that's been very cool. And then we've also been looking into multiple subject monitoring using like MIMO configurations, so separating and localizing to monitor multiple subjects at one time. And then more stretched, challenging situations such as like exercise monitoring. And a project that we've recently worked on is through wall monitoring, so being able to transport your radar sensor around like the edge of a building and be able to tell if there's people inside of it. So that's got defense application and like search and rescue type applications also. So those are all really cool, and this is really exciting research, and I absolutely love it. But there are some difficulties that we've come up to, which kind of brings us to our project here today. So most of the research that has been done in this area, as I've kind of hinted at before, has been done on custom hardware, like hard-coded radar sensors that are built to transmit like one type of waveform in a limited frequency range, or like with very tight control over like things like pulse repetition intervals and bandwidth and things like that. So a lot of times we have found ourselves in a situation where, okay, we're doing this, and now we wish that we had control over this certain parameter of this radar that we have, but we can't reconfigure it easily on the radar sensor that we have, so then we go back to the drawing board and find a new sensor to work with. But Jacob over here is kind of a SDR expert, and he's also a member of our lab, and over the past year we've kind of started thinking in the back of our heads is like, we should start using the software-defined radios as radars for this purpose, so they don't have to constantly be going and looking for new radar sensors, because software-defined radios allow you to very easily reconfigure or just give you all the control that you don't have with those other sensors. An additional benefit that we see to this project is that software-defined radios are pretty accessible, especially like at universities and such. So a lot of people have access to a software-defined radio, and then in combination with GNU radio, it's pretty easy to set this up. And this is like very, like obviously I think this, but super exciting research, and it's very fun application. And we wanted to like do our project in a way that got other people excited about it and was very easy to follow, so that other people in other places can start looking into this also. Because the more people are working on an issue, the more quickly it can innovate, and the quicker that we can actually see it through to something that's used in everyday lives. Because the signal processing approaches still need to be kind of robustified before they're actually implemented in hospitals and such. So some future extensions that we hope to do. What we set up for you today is just a simple, like the simplest test case of vital sign monitoring using just a continuous wave, unmodulated tone bistatic radar. But in the future, we want to start looking at different waveforms and shorter wavelengths. So we're getting some new radios in the lab that will allow us to go into the millimeter wave range and more easily configure MIMO type setups. And then also explore new and improved signal processing approaches, which GNU radio will help us implement those very quickly. And then something else that I want to kind of like emphasize here is that this was like, I mean, no one wants to say this about when you do a research project, but this was relatively easy to set up. Like, this is simple, especially with like GNU radio. We put this together and like innovated on it in like it took a while, but like the actual like demo that we're doing was like a few hours of work just to get this like set up. So it's very accessible, it's really cool, and we want to get other people excited about it also. So now I've talked a lot about background. I'll actually explain the experiment that we did for you. So we used, what we have here today is just an EDIS-USRP B210 and 2 horn antennas, and I'm going to have Jacob sit here, and he's going to breathe, and we'll display it for you, and you'll be able to see his respiratory rate very, very obviously, and then the heart rate will be a little bit more difficult. But the general signal processing approach that we take is we are capturing the complex baseband signal on the receiver, and then we track the phase of that versus time. So if you look at the blue line here on the left graph, that's just the received complex the phase of the received complex baseband signal versus time. So the peaks and valleys of that correspond with the chest expanding and relaxing, and then I'm sorry, it's crackling a little bit. I'm not really sure why. The kind of smaller oscillation, you can see like little twitches on top of the like the higher frequency wave riding on the chest movement correspond with the heart rate. So that's a little bit harder to extract, but you're also able to do it. So the first step in our signal processing approach is to remove the DC offset that happens as a result of like the phase wraps every 2 pi, and there's some like slight motion of the subject that can cause it to kind of shift over time. So first thing we do is we did a polynomial fit to remove the DC offset, and then you can look at that versus time. And then we want to transfer it into the frequency domain, so we do that with a FFT. And in this data that you're seeing on this screen, the subject, if you were to count the peaks and valleys, took 16 breaths in a minute. So when you do move it over to the frequency domain, you see a very sharp peak at 16 breaths per minute, and this corresponds with the respiratory rate. But then a characteristic of the FFT is that you see harmonics at integer multiples of that value. So you're seeing a few harmonics of the respiratory rate pop up in the area that we're looking at for heart rate also. So this is kind of a slight difficulty with our current setup, is that sometimes the respiratory rate harmonics are of similar amplitude as our heart rate peak. But you can still see, so like in this data right here, the subject had a heart rate of 68 beats per minute. And you can see a definite noticeable peak at 68 beats per minute. So it's interesting, but there's still room for future improvements, and we're hoping to implement a lot of the research that we've already done in our lab on using software-defined radios, and then continue to improve upon it quicker in that way. So without further ado, we'll set up our demo for you here. Okay, so we're just transmitting a complex tone, and Jacob's gonna breathe, and the top plot here will just be the phase versus time. It takes a few seconds of lag before it starts to pop up, but you'll see it in just a second. And then the middle plot is the DC trend removed, and then the bottom plot is the FFT of the signal.
So it's just a simple flow graph. You put a cosine in, and you get a cosine back bounced off, and then you just track the phase. And so it bounces every time I move way too much. So there it was for a second there. You saw my respiratory rate. I'm breathing at about 16 to 20 breaths per minute. But then if I actually sit still for about 30 seconds, you'll see my heart rate start to come out, and it's way high right now. So you probably see it come in around 70, 75 beats per minute here. So I'm going to attempt to sit still, which is hard for me because I'm nervous up here. But we'll see what happens.
Yeah, it'll start to come through. So now it's starting to flatten out, and you can see the peaks there correspond with his breaths. Let me know when you start holding your breath. So if he holds his breath, you'll be able to see his heart rate a lot clearer because it's not varied by the respiratory rate. So there you go. Now you're seeing those peaks right there are heart rate, heartbeats on the top plot. So, yeah. So all the little peaks there correspond with heartbeats.
You can see the little heartbeat right down the middle there. In the middle plot, you can see just the heartbeat writing once it's been filtered out and processed a little bit. And then, because my FFT on the bottom is poorly scaled, you can see a peak at the bottom. And if we flip over the output, we'll see it's estimating somewhere between 6 and 16, and then my heart rate there at 70 during that 70 period. Otherwise, it's just making estimates of my respiratory rate. So there's it just chugging along on stage.
Yeah. So we'll keep that fired up there for a minute, but try not to knock this over. Does anybody have any questions?
Hi, I have two questions.
Yeah.
The first one is, why do you choose 4 gigahertz?
Why did I choose 4 gigahertz? So, main reason is that that's what worked best with the antennas, and is about as high as we could comfortably go with the software-defined radio that we used. So the higher frequency that you go into, the smaller here, let me go back to the equation. Yeah, so the smaller distances you can measure, but with larger changes in phase. So as your wavelengths get shorter here in this equation, the very small changes in distance will cause larger changes in phase, which means that very small movement of the heart is going to make a bigger oscillation there. So that's something we want to look forward to more in the future, is going like more into the millimeter wave range, which we're going to be able to do once we get. What? Yeah.
My second question is, how much power do you transmit, and what is the level to be harmful?
Power transmit.
Power level.
Not a lot. Less than a milliwatt.
Do we have more questions? We have some time. Oh, there we go.
Any idea, or have you guys had any thoughts about how you might deal with motion correction, like for a subject who's moving beside breathing rate?
Could you repeat that? I'm sorry.
I was wondering if you have any thoughts on how you would deal with subject movement, like somebody who is moving around besides just their chest.
Yeah, so that's definitely a more difficult situation, is when there's a lot of movement going around. So what this is capturing is oscillations. So a lot of movement is not an oscillation so much as like a jerk or a jitter. So for that reason, a lot of times you can look at the data and see like some kind of big jump or something, and say like, if this happens, that's probably not a heart rate or a respiratory rate. Like that's not what it would normally look like. So we have some people in our lab looking into some like machine learning type stuff to be able to kind of catch when that type of thing happens and then throw it out. But it still needs to be improved upon also.
Another fun method for that is using a range Doppler radar and then picking out a bin that's relatively stable is actually target tracking. But you end up needing an inordinate amount of bandwidth for that, hence the move to millimeter wave for future experiments and pushing it to the limit there.
I know. I might have missed this, but you're not wearing like a metal patch or anything to enhance the reflection.
I have shirt on or whatever.
Okay. I wonder if that, I had a similar question to him, but I think you guys answered it pretty well on like smart ways to like reject like clearly wrong heart rates and or respiratory rates. I wonder if you had something like, you know, like a retroreflector, like an RFID type thing, that if the enhanced reflection might not allow you to I don't know. I just wonder if that would help with you know, rejecting some of those bigger motions, but I'm not an expert in this.
Yeah, so we've actually thought about that.
Can you please move closer to the mic?
Oh, we've actually thought about that a little bit in putting a little gold or similar implant near a heart rate or a pacemaker even style thing to be able to actually improve your motion cancellation or tracking ability for a subject like a human. So we've done some early modeling on how those waves go through, penetrate the chest and are reflected off of it. What kind of other effects aren't we anticipating from the human body and the flesh, as it behaves differently than a lot of other traditional materials that we reflect stuff off and experiment with in the radar community. So yeah, we've looked into stuff like that, and it looks promising for some approaches, but it's also undesirable for other reasons. So you have to balance your approaches there.
Yeah, there could definitely be some benefits, but one of the main got completely contactless nature, which that kind of retracts that element of it. But yeah.
Hey, I have one more question regarding the frequencies that you use. So I know in medical environments, there's a lot of medical equipment ongoing, and some of the things you need to make sure before you get FDA approval to use on a patient is that you're not going to interfere with anything that's, you know, life critical. Have you gone through an analysis of what spectrums, what available bandwidths you could use for doing? I know right now 4 gigahertz works with what you have for demonstration, but for future applications.
We haven't gone too far into depth with that, but like we said today, we're transmitting very close to the range that like Wi-Fi is in, so like that's already allowed, and like you can use that. But yeah,
but it's also an issue to be in those Wi-Fi bands. You get jammed quickly and you struggle. I know that the medical field is pursuing lots of 5G in branch for kind of the Internet of Things connectivity and ultra reliable connectivity, and those bands are actually, until you get to FR2, they're not particularly reasonable for this, because at the end of the day, you really want to be up at millimeter wave frequencies to get the resolution you want and realize the performance for these kind of systems. So as far as I know, the medical field isn't strongly interested in FR2 yet in deployments, but it's a good thing to anticipate, so thank you. Appreciate bringing it to our attention.
All right, you have another question? Okay, good.
Particularly with contactless monitoring, I don't know if you've looked into it yet, but neonates, one of the things that they typically use is adhesives to adhere to the skin, and it's very fragile. For something like this, neonatal unit would be prime focus of.
That's actually how I got involved with this. Is my undergraduate research was in this application for neonatal ICU environments, and our lab in Arizona has started like a kind of a spin-off company that's looking into that application specifically, because you're absolutely right that ECG electrodes often like tear at their skin and make it very hard for the nurses and doctors and their parents to be able to actually hold the babies. So that's like an ideal application for this type of thing.
All right. If there's a short question, we can maybe squeeze it in. Otherwise, I'm going to ask the next presenter to slow. You have a short question? Okay. But like, sorry, Joshua or something, Joshua Mack, I think, is the next presenter. Maybe you can start walking towards the stage.
Have you guys tried benchmarking against like traditional ways of measuring those, and how do your results compare?
Yeah, so in our paper, there's actually a little bit of a discussion about that. So in the radar that we set up, like this is, like I said, as simple of a system as you can set up. And it can get respiratory rate pretty much completely correct. What we said in our paper, we said that we got it within about plus or minus 5 beats per minute on the heart rate. which is pretty decent, but it's not as high as what the PPG what a conventionally available PPG can do at this point. But we're hoping when we start being able to set this up in the millimeter wave range, which is what we have used for most of our actual hard-coded radar sensors, we'll be able to improve upon those results.
Well, we love demos. I think this might actually be the first sort of biomedical demo we had live on stage at GRCon, so that's the first. And for that alone, but also for your great talk, I'd like to get a big round of applause for our speakers. All right, then. Our next presenter is already queued up. Don't have the schedule in front of me, something runtime scheduling. I hope you can introduce the title yourself.
Good to go? Cool. Okay. Hello, everyone. I'm Joshua Mack, and along with me is Serhan Ganer. And today we're going to be talking about GNU Radio and CEDAR, runtime scheduling to heterogeneous accelerators. And so for some background on who we are, we're part of a research collaboration between a couple different universities and industry partners as a part of the DARPA DSOC program. We're thankful to Tom Rondo for kind of getting us a little bit connected in with this community because it has some fun applications for us. And looking at who specifically was involved in preparing the content for this presentation, there's Serhan and myself, as well as Jacob, one of the heroes of the previous presentation as well, for his GNU Radio expertise. So to give some motivation on what we're talking about today, the broad goal that we're working towards as a research group is to enable better use of heterogeneous systems. So everyone broadly knows that heterogeneous computation has a lot of potential in terms of the kinds of speed-ups you can theoretically gain if you're able to utilize these systems effectively and get the right kernels running on the right hardware at the right time. But it turns out that problem of actually doing that management is pretty difficult. So the approach that is taken in the program that we're working on is to look at these so-called domain-specific processors, which narrow the scope of the applications you're looking into to be narrow enough that you can effectively build accelerators for them, because you can't accelerate everything, but broad enough that those accelerators are useful, again, across multiple different types of workloads. And so what we're looking to do as a part of this program is to build a fairly usable domain-specific coarse scale heterogeneous processor. And as a part of that, we focus on the runtime side of things. So you have the hardware design of the chip itself, and then you need some software layer on top to help you actually program and use applications on it. And so the solution we've come up with is a runtime we call CEDAR. It's a compiler integrated extensible DSOC runtime. It's a runtime for general heterogeneous systems, not just the dash chip that we're building, that enables hardware agnostic application development, integration of new software and hardware scheduling policies to manage your hardware resources and task mappings. And then it allows for dispatching of tasks in the runtime to arbitrary hardware IPs that can potentially weren't known to your application at compile time. It's a fairly portable runtime, so it just runs in Linux user space, easy to port to generally, most other platforms. It runs as just a simple daemon process, and then as a part of our work, we've validated it at this point across lots of different FPGA and GPU setups on ARM, Arch64, and x86 systems. And we've found that it's pretty scalable. It supports, in theory, arbitrary mixtures of dynamically submitted workloads all sharing the system. The broad overview is shown on the right-hand side of the screen here, with the left half of this picture being the compilation flow and the right half being the runtime. I'll go into the runtime a little bit more on the next slide, but just worth noting, if anyone is curious, the link for the sources for the source code is down at the bottom here, as well as a ACM transactions paper that we've published. So the runtime model itself is built around a core management thread that, as the name implies, manages the state of the system. So it essentially operates in a continuous loop of monitoring for incoming applications and launching them as necessary, waiting for tasks to be submitted by those applications, and then scheduling them with some user-defined scheduling heuristic. So that can be something simple like a round-robin scheduler. That can be something more complex, an earliest task first, or a neural network-based scheduling heuristic of some kind. But whatever path that task goes through, the way we represent schedulable resources in the system is by having this one worker thread per PE scheduling model. And this is something that broadly we've found in some previous discussions that it's, we believe it's still true, aligns with some of the goals of the GR 4.0 new schedule. But the way you schedule resources or tasks to resources is by pushing work into an input queue for the associated worker thread. And so a task might be a full FFT calculation or a full gem operation, things like that. And then the worker thread for that resource is either bound to the CPU that it represents. So if you're scheduling something to CPU 1, it goes to CPU 1. Or if you are dispatching to a dedicated FFT accelerator or GPU or something similar, then that worker thread takes on a different hat as a management CPU core that coordinates any of the data transactions that need to happen for that heterogeneous compute to actually get done. So on the right-hand side here, we just see an example of that for an FFT accelerator, where the management core configures maybe the FFT point size and whether it's a forward or inverse transform, configures the DMA engine to do the data streaming, and then waits for the task to come back. And then how you actually write applications for this runtime, we've gone through a few different approaches at this point, but what we've settled on for the moment is hardware agnostic API setup, which should be pretty familiar to most programmers. So the way that this ends up working is in your source code, you can write just some hardware agnostic kernel like FFT or gem or FIR, like do a FIR filter. And at runtime, Cedar loads a compatible set of API implementations for the platform that you're running it on. The mechanics are that each of these APIs internally call into Cedar, which pushes a task into the ready queue that management thread oversees, and then over time, the management thread schedules and dispatches tasks to resources across the system. As tasks finish, they are reported as complete back to the user application, and the user app can just continue on its way. So with all of that background of this runtime out of the way, what did we do in this talk? The main goal of this presentation was to take some of these capabilities we've been building and see if we can leverage GNU Radio applications and schedule them across heterogeneous platforms in the same way. So to do that, we built with the help of Jacob, an out-of-tree module that we call GR Cedar, hosted at the link down here. And the rough implementation approach is that blocks in GR Cedar make calls to Cedar APIs. And so these blocks can, of course, be used either directly in C++ GNU Radio applications, or you can use them in flow graphs and convert to C++ with Cython. And then when you run these flow graphs in Cedar, they have the effect of being dynamically scheduled and dispatched to any of the heterogeneous resources that you have available. And so we think that's a pretty powerful capability. A lot of other heterogeneous runtime approaches, you end up making these static decisions about where you're going to run code kind of at compile time. You know, someone analyzes the application and they go, oh, this part is the most suitable for GPU acceleration. We're going to run that on, we're going to put the CUDA call here and run it on GPU all the time. We find that if you want to have a world where you have a heterogeneous system actually sharing resources with other processes, you can't actually know what resource will be most efficient until you've made it to runtime and you're making that decision based on the system state. And one other thing worth noting here is that these binaries are portable because we load the backend implementations in Cedar when you launch it at runtime. The binary of your application itself doesn't contain any of the implementation details of how those kernels are run. And so one example flow graph shown on the right here is just a demonstration we'd done on an FPGA system, a Xilinx CCU102. It had a couple of FFT accelerators and GEM accelerators. And we have one GNU Radio radar correlator application sharing the system with two non-GNU Radio applications of Wi-Fi transmit and synthetic aperture radar. They are being injected periodically. With the first portion of the flow of the Gantt chart we see here shown on the left, we see all three applications sharing the resources and at runtime. And then there's a middle portion where only the GNU Radio application is running. And then in the third phase, the Wi-Fi transmit comes back in and is able to share effectively. So we won't see this demo live, but in a few minutes, Serhan will be showing similar capabilities on the Jetson GPU development board. But before we get to that, we'll talk about the demo that he'll be going through. So the goal here is to show dynamic heterogeneous scheduling of GNU Radio blocks in Cedar. So to do that, we're just going to run a simple correlator application with and without GPU acceleration on an NVIDIA Jetson AGX Xavier dev board. And then we will just monitor the waterfalls generated from both the standalone typical GNU Radio flow and the Cedar-based execution to verify that it's correct. And then we'll see that the tasks on the GPU were being dynamically allocated that way. So with that, we will go over to the other board.
Is it good? Okay. First, we will set the environment, and this will build Cedar and install every API call and it will also build the integration with GNU Radio and also build the install that integrated GNU Radio blocks that use Cedar APIs, and then we will we'll look at our applications Cedar version, where we are using the Cedar blocks for FFTs. And here, these are our FFT blocks that basically uses the Cedar FFTs that will be scheduled in runtime. And this application in standalone GNU Radio is looking like this. We use only the regular FFTs for the GNU Radio from GNU Radio. And then we need to compile this application that uses the Cedar APIs. We first generate the Python code, and then from here we compile it. We first convert it to C and then create the shared objects that we are going to use in Cedar. Here we see the shared object. Let's go to the build directory of Cedar and copy the shared object here. And we have the shared object. Now we will run Cedar here. And on the second terminal, we will submit the application we just created. And at the same time, I will also run the GNU Radio standalone Cedar, standalone application. The right one should have shown the Cedar's execution.
So I think we're going to try and relaunch that flow graph there.
Yeah.
Okay. And then so from there we can see the two different implementations running side by side. The one on the right is running in Cedar, a little bit slower because we have a debug build and a lot of logging enabled to collect metrics about the application going on. But a lot of those metrics you can turn around and use those for things like training data for neural network or imitation learning based schedulers.
Now this one was only using CPU. Now let's kill this one. We run the plot.
And so just to show basic functionality, we had started just with a CPU validation that we're able to just port an application to run on CPU in Cedar at all. And now Serhana is going to go ahead and do the CUDA enabled build. And we'll see the GPU acceleration there.
This time on the right, it's using GPU also together with the CPUs.
And it's worth noting that that was still the same flow graph as we had been using previously, just running in Cedar loaded with a different configuration. And now, just to really convince ourselves that this actually did run on GPU, we can look at the Cedar scheduling logs to see where all of the tasks were dispatched and check that some of them actually did end up there.
So here we see that some of the FFTs were scheduled on the CPU and some of them were scheduled on the GPU, and this is decided on the runtime. Slides.
And with that, that's the end of the live demo here. Going back to the slides, just to show a quick summary. Okay, so yeah, we've shown Cedar, a name that maybe you're tired of hearing me say by now, and showed that it's a Linux-based, a runtime for Linux-based heterogeneous systems, along with a proof of concept out of tree module that shows how to integrate GNU Radio applications into our runtime. Some future directions. Right now, that out of tree module only has the FFT block, so adding more blocks within that would be nice in the future. And alongside this, we would love to continue working with the community to see what opportunities there are for incorporating this in the GR 4.0 new schedule work. But with that, we'll end the talk here and see if anyone has any questions.
Do you have a question, or are you just lifting your hand? I don't think you have a question. There we are.
So a big gotcha with heterogeneous computing is timing. And you say offload the data, and then you just sit there and wait for it to come back. And so yes, you're using less CPU, but you're not actually processing anything any faster. Or you just keep sending data off and you overrun buffers, or you have other problems. So does Cedar do anything to help the programmer make good choices for offloading and waiting?
I think the power that it gives is it lets you test out different scenarios and see what works in your use case pretty trivially. So it's not difficult to implement maybe a CPU only scheduler or a scheduler that tests out different scenarios and allows you to do that kind of trade analysis. The exact specifics of how to handle efficient data transfer do, I think, vary based on the platform you're running on. And so we don't have a completely abstracted answer for that, but that could be something along the lines of, I know there's been zero copy buffer work presented in the past, or removing the double copy problem, things like that, that could potentially be integrated as potential approaches to solve this.
Do any more questions? Okay, I have a question. So one thing I didn't fully understand in your demo is, like, what is the actual input to the scheduler? Is it like the entire flow graph, and then it picks out the individual blocks that can be shuffled around?
It would be individual tasks. So one task might be a full FFT call, but each time the GNU Radio block's work function is called, that pushes a new FFT into the queue for Cedar to schedule.
Okay. So there's basically a hook that figures out when those tasks are being called.
Yeah, that's somewhat on the bottom right-hand side of this plot. The dash FFT that is in the user application is roughly equivalent to initializing a pthread barrier and then sending this enqueue kernel is a magic function that links within Cedar to push a task to the ready queue with all of the necessary arguments. And then the user application waits for completion, or we have non-blocking APIs that if you know something is independent, you want to run things in parallel, that's an option as well. But
Okay, but the GNU Radio 3 scheduler is still running then, and then I'm curious if you do it like that, are you like gonna have like some weird effects of like the the TBB scheduler and your task dispatcher like fighting each other or like stepping on each other's toes or something like that?
I think there's definitely opportunities for that, particularly given the way that all of these worker threads we are setting their affinities manually in ways that may somewhat conflict with how. I mean, it's ultimately the kernel scheduler still scheduling threads at the end of the day for us at the moment. So I think there's some opportunity. There probably are some possible ways that could conflict, but I don't think we've explored this integration enough to really say what those are.
But I mean, you've mentioned GNU Radio 4, and I think that's where we can see more like opportunities to employ something like that rather than GNU Radio 3. We have time for one more question, I think. Oh, there's one over there. Perfect. Let me just walk over.
So apologize if I'm not up on some of the lingo, but I'm wondering how the scheduler kind of decides what to do at runtime. Like, if a task is submitted, is it figuring out how long that task would take on all the different architectures, or is it just like submitting it to the first thing that's open, right? Like, I guess I'm wondering, like, how does it know to submit it to a GPU? Does it know that that's going to be faster per se on the GPU, given all the overhead, for example?
That depends on the algorithm chosen, I guess. So when you launch Cedar, you choose which particular scheduling algorithm you want to use. You can just use, we call the simple scheduler is a round robin approach, and it just goes through the entire list of resources and attempts to find something compatible with the task you have, because there's also chances that you have a gem task and a round robin would try and put it on an FFT accelerator, and it goes, no, that's not compatible, so it moves on. But there's a lot of opportunity for design of more intelligent heuristics, and we have some details of that in the paper in terms of work from our collaborator at UW at Wisconsin in doing an imitation learning based scheduler of a more complex kind of smarter policy, but using imitation learning to lower the runtime complexity so that it also meets real-time needs.
All right. We could squeeze in another question, but I don't see any hands raised. Last chance? No? Okay, well, then big round of applause for our presenters. Okay, while the next speaker is setting up, like I think a couple of people here are doing CTF. Anyone doing like catching flags here in this room? You guys, maybe? No? Kyle, excellent. What's your score? Oh, okay.
Okay. Testing 1, 2, 3. Okay, perfect. Hello, everyone. My name is Matthew Finger. I'm a senior in electrical engineering at Weber State University, and I've been given the honor to talk to you all today about our open source antenna pattern measurement system and the software-defined radio-based student research and development that has gone into it. So I will break this presentation down into 4 parts. We've got the background, the different phases that it's gone through, the application. I'll show 3 different antennas that we've tested with our system, the upgrades that the system has gone in recent years, and then finally some future work and summary of the entire project. So the background of the projects all started in 2011. There was an article written in the IEEE Antenna and Propagation magazine about 2 students that graduate students from the University of Illinois that created a antenna pattern measurement system using 2 of the old Linksys routers. And they used the Linksys routers uploaded with open source DDR-WRT software, where the routers would handshake and then measure the signal strength of the antenna under test. And then the router would rotate and do the same thing until it had the full 360 degrees of its azimuth measured and then patterned out. And so one of the professors, Dr. Hearn at our university, saw this and wanted to recreate it in one of our labs. And once the entire project was recreated, we wanted to update it to kind of today's standards. We wanted to replace the Linksys routers with software-defined radios, the motor controller with an Arduino, and use symmetric belts and 3D printed materials to make it all more accessible and portable. And so Weber State University wrote to the Utah NASA Space Grant and was given a grant to kind of move this project along into the next generation. And we wanted to use it for kind of outreach and loan opportunities with other universities. So this was in phase 1 in 2018. We had a master's student named Dan Newton create this first system where we have a directional antenna pointed downrange at our antenna under test. And the antenna under test would measure the noise, the ambient noise, and then we would send a band-limited noise through the directional antenna, measure it from our antenna under test, take the average with the from the time, and compare it to FICO simulations. And we have the top here, a monopole antenna, and the bottom a patch antenna to have different kind of antennas to show the measurement of our noise cancellation system versus our simulated system. And then from there, we had a second master's student pick up the project, and he wanted to incorporate coherent AM detection as opposed to measuring the ambient noise and then measuring the signal. And he wanted to just do it all at the same time. And the key takeaway is to achieve that coherent detection, we needed to tie the clocks of the transmitting software-defined radio and the receiving radio together. We used 2 hack RFs, and since our software-defined radios are in close proximity, we were able to tie their clocks together physically, and that way we didn't have to search for a software solution to that. And then we used an Arduino Uno programmed with the G code to use our stepper motors to rotate on the azimuth. And it's all controlled through a laptop. And we did a simulation in Multisim here to show the concept of our coherent AM detection. The big takeaway here with this graph is the top is our input, the bottom is our output, and the modulator and demodulator are tied together in a common source, effectively tying their clocks together. So in 2021, we wrote to the Utah NASA Space Grant and received additional funds to continue our project. And we had a mechanical engineer step up and redesign the masthead using all 3D printed materials, kind of going with our direction of having it more portable. And as we can see, the masthead all comes apart and fits nicely in that suitcase. And we also were testing out in various lab rooms and parking lots and things like that to show the measurements were similar regardless of the kind of noisy environment, and that didn't need an anechoic chamber to get close to our validation simulations. So we'll move on to the second part. I'm going to show just a couple of antennas that we've tested with it. The first was the microstrip patch we have up in the top there. That is the actual physical microstrip patch picture. They have the FICO simulation of it, and then we have our FICO simulation versus measured in a noisy environment. And again, the patch a lot of times is seen in GPS and space communications. This one doesn't have a ground plane, and that's why we have a kind of a reflection of our main lobe down below. The second was the quarter wave monopole. It's the kind of iconic butterfly wings of the antennas, and it's mostly seen in handheld radios. And once again, we have the pictures of the actual physical quarter wave monopole antenna we made, the simulation, and the results. And then finally, we have our end-fire array Yagi prototype, which was built and simulated. And this is to test the directionality to make sure that we have kind of the GPS antenna, the handheld radio antenna, and the directional antenna. This was used a lot in kind of television back in the day. So that's where I came into the project. A lot of the software was from before 2018, and it needed to be up to date because we wanted to port it over to a Raspberry Pi, and Raspberry Pis use a Raspberry Pi operating system named Raspbian, which is essentially a Debian offshoot. And so we wanted to update the Linux operating system to that Debian version, update the Python protocols and the Python code, and then update the GNU radio companion block flow diagram. One thing with each kind of step is to show that it is kind of able to go into the forward through generation of code. It all can be made so that if there is a update that requires different syntax, for example, that a student would be able to go in and change the code and update it so that a single update isn't going to effectively destroy or cause the entire system to stop working. So with the GNU radio flow graphs here, we had our transmitter model going into a multiplier, and then our Osmocom sync, which is the sync required for the hack RF. One thing that is nice is that once you've compiled your GNU radio code into the Python and you have kind of modeled that as a Python class, you're able to take any of the variables in there and reassign them. So for example, in our system, we have the frequency of our modulator as a user input. So therefore we can take multiple frequency measurements. So go from 2.4 measurement, 2.41, 2.42 to see the frequency response kind of over a broader range. And then here is our receiver model. Again, once coming in from our Osmocom source into our multiply, upgrading from the later levels to the current version of the GNU radio. One thing that we noticed was added was the windowing on the kind of low pass filters, but everything in the Python code defaults, luckily. So if you did not go back and recreate a flow graph at a later time, it would just default. It would have a default value associated with it. So I think the kind of, for example, was the windowing was a Hamming window, and we changed it to a Kaiser because we got slightly better results with that. And then so once all the software was up to date, we took new measurements across a laptop, and we made sure that the code was both 64 and 32-bit compatible, and it made multiple backups here. So we have, once again, our monopole, or our butterfly wings on the left, and our patch antenna on the right. And that brings us to the next step of the project, was to get the entire system to be running on a Raspberry Pi. And the main draw for the Raspberry Pi was the SD card. Once you've set it up once, you're able to create an image of that SD card and then flash that SD card as many times as you want. And all you'd have to do is plug that SD card into the Raspberry Pi to get the full system up and running, as opposed to getting a laptop, installing Linux, making sure all the dependencies are up to date, Python, GNU radio, again, update the dependencies. And so we just wanted to streamline the process a lot more. One thing that was of concern, though, was the USB ports. We used 2 hack RFs and the Arduino controller, right? There's 3 USB ports. That's not counting a keyboard and mouse. And we didn't want to connect to a hub because that could potentially add more noise to the system. So we would eventually transition into a touch screen with the keyboard in the 4th USB to avoid that. So our first attempt was with a Raspberry Pi 3. It was more readily available, especially with supply issues nowadays. So we got it a lot earlier than the Pi 4. However, we noticed that the measurements that we acquired under the Pi 3 were extremely noisy, as we have the monopole once again on the left and the patch on the right, and you can see how kind of jarring all of the different measurements are from each other when they should be kind of a smooth curve. And we were also getting memory errors, a DRI2 failed to authenticate, where 1 in 10 times of running the program, it would effectively crash, and there would be no way to track down which part of the memory was crashing specifically unless you hard rebooted the Pi. And so between the kind of data acquisition and the errors crashing the program, we unfortunately did not continue with the Raspberry Pi 3, but we had a Raspberry Pi 4 already ordered, and when that had come in, we had redone the measurements with the Raspberry Pi 4, and we see the comparison between the two. The Raspberry Pi 3 is once again in the blue, and the Raspberry Pi 4 is in the orange, and it fixed the issues that we were having with that very jarring and noisy hardware, as well as the memory issues that were occurring. One thing with this test is we wanted to make sure all of the variables were as consistent as possible. So we made sure that it was the same exact antenna that was used, the same location, the same distance from our transmitter to our receiver, and we went as far as using the same SD card between the Raspberry Pi 3 and 4, where we would run the transmission or the test as under the Raspberry Pi 3. We would take the SD card out, unplug the USB ports, plug all of everything in the Raspberry Pi 4, plug the same SD card back in, and rerun the program. And the kind of results, I guess, show for themselves there of how much better the data acquisition is for the Raspberry Pi 4 versus the 3. Next, we had the directional antenna. We noticed one problem when going from the legacy code to the newer code was that effectively the more directional antennas were causing large side lobes that we couldn't explain at first. But when we looked into the data, everything along the main lobe of that first one was exactly the same. And since we're normalizing around the directionality or the maximum signal strength, it effectively caused the side lobes to become much larger than what they should have been. We went through and tried to change a bunch of receiver settings to see why we were effectively cutting off data, or that we'd peaked, or one of the two. And it wasn't until we tried messing with the transmitter gain that we noticed that when we turned the transmitter gain down in the newer code, as opposed to the older code, that we would get the directional antenna measurement that we were expected there in the orange, as it has the kind of full main lobe, and the side lobes are much better down to proportion, as they should be. So that brings us to the future works of the project. One thing that we want to incorporate, like the second half of my senior project, is to get a 3D, go from a 2D measurement to a 3D measurement. We have kind of a new base that's underway to get the elevation control. As of right now, we only have that azimuth control. And once we have that elevation control, we'll be able to take our antennas and map them in a three-dimensional plane. And then there's also mechanical improvements, sensors, and we have, this is just kind of a list of other things that can be added on to the project. And I'm sure there's many, many, many more that people can think of as time goes on. So this brings us to the summary. We wanted to really emphasize that it is an open source, it's student maintained. A lot of antenna measurement systems require a professional license and have a professional team come and set it up. And if there's an update that causes something to crash or a sensor to not work, you have to then pay that professional team to come again and work on your antenna measurement system to get it back up and running. And sometimes they can't even get it back up and running and have to replace the entire thing. So this entire program is student maintained. Again, it uses Linux, GNU Radio Companion, Python, Arduino, 3D printed materials. It is all something that you could give a student or even someone just in the amateur radio field, and they would be able to kind of work on it and fit it to their needs. It also shows that this, just reiterating one more time that open source, it's gone from a 2018 version to now a 2022 version. So we've updated software already on it, we've updated hardware, and to show that the process will kind of grow along with time as 3D printed materials become better, or the software, because I know the GNU Radio has 4.0, so I'm looking forward to diving into that as well, and to update that. And then all the measurements were done kind of in a noisy environment, and we'll eventually be doing them kind of in an anechoic environment to compare the two. Some acknowledgements. We'd like to thank the Utah NASA Space Grant for sponsoring us to get it all started and kind of got us to where we are today. Moog Industries donate a lot of the absorbers that we use in our tests. And then Weber State University, we had Dan Newton and Taylor Hansen, the two electrical engineer master students that worked on it before me. And Ren Fisher was the mechanical engineer that worked on the 3D modeling of the new base mast. And then Christian Hearn and Justin Knighton were the two professors that have kind of advised us along the way and helped us kind of bring everything together. Was there any questions?
All right. So we can maybe take one question while our next speaker, Chris, can move towards the podium. Are there any questions? Where's our next speaker, Chris? Oh, there we are. Okay. Yeah. Okay. Actually, so while he's walking up, I have a question. Do you have any theories where that noise came from in like the Raspberry Pi 3 measurement?
On the Raspberry Pi 3s, we read a lot about how people were getting essentially popping a noise depending on when they listen to audio, depending on the USB ports. And so our main theory was going to be testing the USB ports as to kind of isolate that noise down. But when the Raspberry Pi 4 came in and we saw that it had effectively eliminated that, we didn't want to do extensive testing on something that was effectively out of date.
All right. Well, thank you very much, and a big round of applause.
Thank you.
All right. Can you hear me okay? Good afternoon. My name is Chris Poor. I'm from Assured Information Security, and today I'll be going over Fissure, the RF framework. I think you'll really like it because it's meant for everyone, so there's something there you'll find to your liking. I'll go over what it is, some of the core principles. We'll go into a little detail about what each component does, how much GNU radio integration is actually in there, and I'll talk about the roadmap, what we're doing in the future, and how you can contribute. So the main point of this talk is just to introduce you to the software and to tell you how to talk to me in the future about your ideas and how we can make this product even better. So what is Fissure? It's an open source RF and reverse engineering framework. It contains hooks for signal detection, classification, protocol discovery, attack execution, vulnerability analysis, automation, AI, ML. It does a lot. And it also kind of consolidates all things RF. So that's software modules, radios, protocols, signal data, scripts, flow graphs, reference material, third-party tools. It's really become a source for keeping everything together in one place. And it's real nice for people to get set up with something that just works right off the bat. So the main theme for Fissure is that it's meant to speed up the characterization of signals and the identification of vulnerabilities in protocols, waveforms, and devices. That's kind of what's inside the tabs of that GUI. So on the right is our different pictures of those tabs. It's just one big main GUI with a bunch of tabs that do different features. And it's written mostly in Python and PyQt, and it has support for legacy systems for different versions of Ubuntu and Python and PyQt. So it's trying to make it easy for just about anyone to get up and get it installed and get it working. And it comes with a out of the box, and I hope someday to be a completely pain-free installer. I understand there's a lot to it. We're working on everything we can. And it's meant for everyone, in my opinion, for experts, for beginners. It's designed so that you can go in and edit the pieces on your own and make it suit your needs. It's fairly new. It's only been out a month and a half. We were at DEF CON on August 12th at the Demo Labs. Some of you were there. I've seen you there. So thanks for going to that. And There's also a video online from the Griffith Institute from like a year and a half ago. That's kind of outdated. You know, a lot has changed since then, so I'm not actively telling people to go watch that video, but it's there if you're Googling for it. And we were also at another C4 Cyber conference. But the main way to get to Fissure is the GitHub page. And if you want to leave comments, you can go to the discussions page. You can write something in the issues. I'm on Twitter, so you can follow the status of the project there. There's a Discord we set up. That is a great way to just talk directly with me. You can get to that from the README. Then on chat.gnuradio.org, my username is cpor1. If you direct message me there, I will get it and I'll see it and I can respond to you. We made a Reddit, for what it's worth. And then in the future, more documentation and videos and user manuals and APIs that aren't already included in under like the help menu will be located at my company's website at ainfosec.com. So that's coming up short term. To understand Fissure, it's kind of important to have some context about where I'm coming from. I'm an electrical engineer at a cybersecurity company, and we do a lot of different things, as you can see there listed. I've worked on RF projects my entire career. I'm constantly jumping around different technologies with each project. It's fun. It keeps things interesting. I'm always going new places and seeing some pretty cool things. But I also work for a small team that's responsible for characterizing systems, assessing security, exploiting and interacting with targets, performing research, and developing tools. And we develop these tools and we do these cool things. We go around and we teach people and try to just show our knowledge to other people so that you can kind of see why a tool like this is important for me in my daily work. So I use this tool all the time. What is Fissure? It's frequency independent SDR based signal understanding and reverse engineering. We needed a word that started with F, and the guy that came up with it wanted to make it like a literal pain in the ass to do a Google image search on it, so I apologize for that. It started from a 2014 project that was responsible for designing a flexible system for automatic RF device assessment. And since then, we've dedicated internal research and development over years to make it more of an in-house lab tool. And now we're releasing it to the public. What does it look like? It's a PyQt GUI, like I showed you earlier, and it has several dedicated Python components communicating to each other over a network. It uses ZMQ and it talks to a central hub, which kind of passes the information along. There's a nice YAML schema for input and sanitization and air handling. So if you have a new component and it has clear inputs and outputs, you could make a nice simple Python wrapper and a YAML file, and you can instantly add it to this framework with very little work. Why are we extending it to the open source community? Well, I'm doing it to help people. I think this software is going to help a lot of people. It makes all our jobs easier. It brings in outside knowledge to me, so it's kind of dumb for me not to release it, in my opinion. And I'm hoping it benefits future generations and has a bigger impact, bigger role in education. And again, revolutionize engineering and cybersecurity. I kind of feel like in the cybersecurity world, the RF and wireless aspect of it is kind of underrepresented. And I think this will help raise it up to the rest of the level of everything else. Fissure is pretty broad, but as long as it kind of follows these elemental principles, it can go into Fissure. Again, to speed up signal characterization, help with identification of vulnerabilities and protocols devices. We also want to have other people's tools be easily integrated, utilize commercial SDRs to help as many people as possible, be a test bed for AI and ML, be flexible, easy to use, helpful visualizations, be modular and have things communicate over a network, and just be simple, transparent, and easy to understand. So Fissure is a framework. It's not a complete product. It's not finished. It's going to look different over time. It's only been out a month. it's filled with examples of how to do things, and you can kind of use those examples to see what I'm talking about, and you can contribute your own upgrades and maybe different features that you want to see, and use it as a guide for now. Everything can be improved. Nothing's really truly complete, and more can be integrated. And I require the feedback from the community to make it better. It's there for you to work with and improve. There are hooks for automation, like everything communicates over Hub, and it's there. But in the meantime, in the short term, I kind of want to build up the capabilities to make it do some important functions before you start trying to automate things that aren't there. Fissure's meant for everyone. I think experts can expose their cutting edge solutions. It's a place where you can expose it to a wider audience. Professionals can use it to perform their daily tasks. Educators can help teach. Students, hobbyists, developers can learn things that they may have not known about. There's a lot of different topics in there that you can peruse and kind of see what's going on. So I'll quickly cover some of these components. I'll talk about what's in there now and what I'm looking for in the future. So one of the first things you do is you try to go into an environment and learn something about it. Maybe find a target device or a signal that you want to look at for more analysis. Right now, there's a very slow scanning detector built in where you can set up different search bands and it'll slowly scan the spectrum. It's not super useful, I'm telling you that right now, but it will report back power, frequency, and time, and you can use that kind of information to pass it to other components. Now, in development, I got a signal conditioner, a feature extractor, a protocol, emitter classifier in the works that I'm working on. And the idea behind those is to isolate the signals, extract features like, frequency, bandwidth, modulation type, and then kind of take a stab at identifying protocols emitters using AI and ML techniques. That's kind of in the future, but that's what it's going to look like in the future. And I'm also interested in fast scanning components like a HackRF sweep or RTL power techniques to replace that slow scanner or have another option to scan. And it's going to be a place to swap and compare AI ML techniques. Protocol discovery. So you take your information from those signals and you try to produce a bit stream from that knowledge, from that target to a bit stream. And there's this concept of recursive demodulation where you load a flow graph with some knowledge of your target, and then you kind of slowly go down and maybe you figure out more about it and you load another flow graph. Maybe there's some confidence about which flow graph you're going to load next. So that's the idea behind demodulating unknown signals. And I know that's a very difficult, challenging problem. But right now, there's only just the demodulation flow graphs, which is kind of like the last stage where you know what the protocol is, you run the flow graph, it spits out a bit stream. So right now, that bit stream goes into a circular buffer where you can slice it up, look for preambles, look for CRCs. It's most useful for fixed length messages, but it can be changed to do things that are different lengths. There's a data viewer where you can take those bits, turn them to hex, apply them to things in your library, see how well it fits. There are custom Wireshark dissectors. There's a CRC calculator where you can do common algorithms or do like a reverse lookup for finding the polynomial. In the future, I want to build out that recursive part, do more work with pattern recognition and variable length messages. Attacks, there are different types of attacks. You can do Python 2 and Python 3 scripts. You just put a simple header on your file and you can change the default values and just click start and it launches the attack. You can do flow graphs with and without GUIs. The attacks are meant for wireless or wired applications when you think about it, because they're just scripts. You're just running scripts. So you could be on a network, maybe you have a bunch of exploits you want to run. You can do that over a wire or wirelessly. There are multi-stage attacks where you just string together a bunch of single-stage attacks and they just go in a loop. There is data field fuzzing. So if you have things already in your library, you can check fields, choose random or sequential fuzzing, specify the ranges, and each message it generates, it will recalculate the CRC and spit out a new message. There's also flow graph variable fuzzing, where you select the flow graph and you can choose the variables in that flow graph, and as long as it has callbacks, it will fuzz those variables. In the future, I want more attacks, more hardware support. Right now, there's just examples for different types of hardware. It's not full for every piece of hardware that's supported by Fissure. And then there's no vulnerability analysis piece yet, where if you're throwing an attack at something, how do you know it worked? How well did it work? You know, that piece, that could be put in there as well. IQ manipulation. So there, you have the ability to launch live inspection flow graphs with GUIs. You can look at things like waterfalls, time slots, or time sinks. There's a lot that you could add to that. I've seen some things here, you know, this week that I'm thinking about adding to it. There's a record and playback feature right in that section. You can view data. It's really useful for cropping data with just a couple clicks. You can record something, crop it, convert it to different data types, perform analysis with a couple clicks of buttons. And in the future, I want more measurement, radar data analysis, filtering capabilities, better inspection flow graphs. There is an online signal archive. It's pretty primitive right now. There's just a couple files in there where you can just click on it and download it from online. And then you can set up playlists to test systems, and it's also useful for testing Fissure itself. So you can select a radio for the playback and then feed it back to like the earlier component where you're doing target signal identification. So you can use it to test itself all in one package. In the future, I gotta figure out a good standardized metadata format, something like SIGMF, create more data sets, use existing data sets, figure out how to best import and export these kind of things. There's a packet crafter for crafting things in your library. You can go in, change values, calculate the CRCs, save them to file. You can construct sequences of messages and save them to a file. There's SCAPI integration for Wi-Fi. So if you're already in monitor mode, you can just select a Wi-Fi message, view all the fields, click load, start, SCAPI's transmitting. So in the future, more protocols and packet types, maybe some links right to the attacks from here. Third-party tools. So this is kind of the unique thing for Fissure, is that it comes with like 100 different third-party tools with the installation steps right there in checkboxes. So this is real valuable for someone who's never done this kind of thing before. And if it worked, it turns green. If it didn't work, it turns red. And most of them can be accessed from the menus under the tool menu bar, and then standalone flow graphs exist as well. So you can just load those up and play with them and not mess with the rest of Fissure. The third-party tools are, they'll either just launch the application or they'll open a terminal with an example command for how to use it. You could also load up online tools, maps, calculators, databases for things. In the future, I want your input on how I can add more things, more different types of things, different protocols and applications. The installer can always be improved. I'm learning that. It's never really going to be finished. And I'm also interested in a Docker alternative because there's a lot of software here and it's not going to play nice with your existing system. So it's best to do this on a staged computer starting fresh. There are lessons in there. They're written in Markdown and HTML. So if you go online and you look at the lessons folder in the repo, you can load up, for instance, how to take the ham radio exam. I took it this year, and my favorite tool to use was Anki. It's free, and you just load in the whole question pool and quickly go through all the questions. So that's nice. But then there's other topics there. I'm hoping to expand this and use it for education and tie it back into Fissure, say like, do this step in Fissure, see this result. And I think it would be a great tool for helping people learn about all kinds of topics. What does GNU Radio do? Well, it launches all these different types of flow graphs that I mentioned, and it passes data back to Fissure in several different ways. You can change variables before running the flow graph. You can change variables while running the flow graph. It's a little different right now for running a flow graph with and without a GUI. If it has a GUI, I can't really change it before running the flow graph yet. So every variable you want to change has to happen through the widgets in the GUI. But Fissure is supporting versions 3.7, 3.8, 3.10. They're all separate branches, so I don't have lots of copies of flow graphs all in one repo. The auto tree modules are pulled from the owners of the repos, so they get cloned every time you do that git sub module command as part of the install. So that's going to that needs to be monitored just in case those repos change over time, like they change the branch name or something like that. And I'm always looking for better ways of using GNU Radio. There's a lot that I'm not doing right, I feel like, and I could do better. And I got to keep up with what's coming out in the new versions. Next, there's a lot of room to evolve as far as the governance model. Right now, it's kind of just founder leader, but I'm working towards making it a corporate backed model. And there's nothing stopping it from being a duocracy where if someone's contributing and they have good ideas and they're actively doing pull requests and things like that, they can be part of this project. I'm always looking for more funding avenues. It speeds up development for the project, establishing more ties with education. In the short term, look for more documentation at the AIS website. We'll be working towards improving the code, testing more hardware, expanding the lessons, the certain features that need to be implemented. And then in long term, maybe move towards more of a sensor node deployment scheme where you're not just in one geographic location, but you can set up multiple sensors that feed back over the network. And I'm not looking to reinvent the wheel in any way. So if I know that all these topics have been done 10 times over by the community at large, and if there are existing solutions out there, I'd rather wrap in those solutions than try to do it myself. So it's important that I get your contributions. So how can you contribute? Well, you can show your interest. That's the most important thing that you can do for me right now is go on the repo, star the repo, join the Discord server, follow on Twitter. It makes it easier for me to go back to my company and say, look at all this interest that we're gathering. And I can go to different customers and say, look at all this interest. And it's more likely to take off if you do that right now. You can contact me. The Discord's a good way. The discussions page is a good way. Suggestions. I need all these suggestions for all these topics. There's a lot of knowledge here, and just pick one thing and send it to me, and I'll be very grateful for that. And you can collaborate with AIS as a professional thing, or you can just do it on your own individually on the repo and things like that. And if you're really into it, you could submit a resume to AIS for full-time employment. We do a lot of cool things. This project is fun to work on, and it has an immediate impact on people's lives, so that's something to look forward to. And with that, I'll take questions.
Thank you for the talk. I have a question. Were there things that you found that had those features been in GNU Radio, it would have made the integration easier? Or features that were missing from GNU Radio that were...
Well, yes, if GNU Radio did more, if more was built into it, that would be nicer. But I mean, a lot of the pieces that I'm writing for working with flow graphs and things like that, I'm using GNU Radio. I'm not using third-party pieces other than like out of tree modules and whatnot. But there are things that are more difficult than others to work with. And I'm probably just touching the surface of what GNU Radio is actually doing. And there's probably better things I can do to improve my software. So I need to learn more. I need to hear about more that I could do.
Thank you.
All right. Any more questions? So I have a question. So there's some other tools in the sort of RF security world, but like they seem like yours seems more encompassing. There's like fuzzing tools, etc. Like have you like compared like have you compared like Fisher to those? Like we had a talk about RF fuzzing like I don't know, like a few GRCons ago, but I've forgotten the name of the tool. Like, are you like sort of aware of those projects and like, so what's the relation between Fisher and like other RF fuzzing tools, or any other like security related tools?
Well, there's tons of tools out there, and I'm aware of a lot of them. There's hundreds of tools, but Fisher is unique in that it puts everything together in one place. So I have this software that allows you to do everything in one place. I know there are dozens of other things that are similar, but nothing quite fills what this does. Like there are VMs out there, there are lists of tools that you can install. There are individual things for decoding messages and figuring out protocols and things like that, but it's not all in one place, and it's not easy for someone to just go in and add something new or contribute or change something or see the code. So it does a lot of things that other things don't do. But for fuzzing and things like that, I haven't really seen a heck of a lot that's useful to me and that's easily installable and things like that. So I don't know. I'll have to look more into that.
And have you been able to find any flags with Fisher?
I haven't had much time to do the CTF, but I will be trying to do it. And that's one thing when I do all these CTFs and things like that. I see how people solve them, and I take those lessons and I try to put it into Fisher. Like I built a Morse code decipher in there for like the DEF CON CTF and stuff like that. So the more I learn about how the CTFs work, the more I can put it right in the software.
All right. Any other questions? Okay, there's no more questions. Then we're going to start with the lightning talks in 3 minutes. Oh man, first line here. Oh, okay, perfect. I do not have an announcement to make, but we will still start the lightning talks in 3 minutes. Let me see. Okay, I don't have the schedule in front of me. First, give a big round of applause to Chris Poort, and then I'll. All right, we have 3 lightning talks: Analog Devices, Periton Labs, and Andrew Avtushenko. 5 minutes each, starting at, yeah, we can start now, right? I think that's okay. All right, we have John from ADI. Yeah, perfect, there you go. Yeah, you can just go ahead, set up. Do you need anything? Like, you need a mic at least, so please stand on the stage where we can point the camera at you.
Okay, I can start. Okay. Hello, everybody. My name is John Kraft. I work for Analog Devices. A couple of years ago, I did a GNU Radio workshop where I used some simple hardware to explore phased array beamforming principles. So these were things like steering angle, grading lobes, tapering, beam squint. Then we did some monopulse tracking where we locked into an RF source. So that workshop was recorded and it's on the GNU Radio channel somewhere. But the workshop was just things that I was trying to learn and experiment with, because I think, like a lot of you, I think the best way to learn something is to do something, right? But, and I heard from several people or universities that have followed that presentation, and they're trying to build up their own hardware and do some prototyping and exploration with phased array beamforming concepts, and which has been great. So at Analog Devices, we wanted to do something to make that easier to use and much more powerful. So with the help of many at ADI, we're doing this hardware and software package called AD-ALM Phaser. It's an 8-channel linear receive array with 2-channel switch transmit, and it can do phased array comms or radar at 10 gigahertz. It's this little guy here. So it mates up with a Raspberry Pi on the front end that kind of does our SPI transactions and uses the Linux IAO operating system or drivers. And then it's got Pluto on the backside here. This is the Rev C of Pluto that has 2 transmit channels and 2 receive channels. So it's in this little nice little attractive stand that mounts like this. And for the radar system, it has a 12 gigahertz ramping synthesizer, so you can easily create various frequency ramps and send that to the LO of the RX and the TX mixers. All that's on board this RF board here. So it's all very, very easy to use. Right now, we're putting all the information on the website that's listed there, wiki.analog.com/phaser. And for more information, that's where you can go. That website isn't complete yet. We're adding some lectures and labs to it to kind of flesh out how to use this and what it would look like and what are kind of some of the things that you can do. So we'll probably have like half of the material is in there so far, and I just have to record some more episodes and do that. We hope to formally release it by the end of the year. You know, I don't know exactly what the price is going to be. It's weird in this COVID time where, I don't know, everything is just weird. So I think the price will be around $1,000. This demo is also operating at the Analog Devices booth. If you want to stop by and take a look at it, we can show you some of the things that it can do. And we're really hoping that others in the open source community take a look at it and might eventually share some of their own labs and lectures that they're doing using this hardware. We'd love to support that. So I hope that seems interesting. Please reach out to me or stop by the booth. If you like that idea and want more information, you can reach me at just john.craft@analog.com. Or like I said, you can stop by the booth and we have this up and running.
We don't usually do that, but like we even have time for a question, like if there's one. You have one here? Wait.
Commercially available by next spring, January?
Yeah, I mean, we have a bunch of them now. So, I mean, they exist now. They're just not offered for sale yet. We got to do the rest of the paperwork and stuff around that. So probably, you know, November or December. Yeah.
Any other questions? If not, oh, sorry, we have a question.
Curious if there are extra elements on that board and if there's like any subarray or anything like that.
What was that?
The elements on that board. I don't know if you can talk about that at all.
Oh, yeah.
Regarding like how many.
Oh, yeah. Yeah, it looks like there's 32 antenna elements on the board. But the vertical columns are Wilkinson summed together for greater gain and directivity. And so really you have 8 linear elements and they're organized into 2 digital beams. So there's 4 elements in one beam and then 4 elements in another beam. And by doing that, we can do the monopulse tracking technique where we take the sum and the delta, and then we look at the phase difference between the sum and the delta lines, and we can do, you know, that kind of adaptive amplitude monopulse tracking algorithm. Okay, yeah.
Okay, cool. Right. So,
thanks, everybody.
Yeah, thanks. Another round of applause while Rob steps up on stage.
All right, good afternoon, everybody. My name is Rob Miller. I am a research director at Paraton Labs, and I have to say we are very proud to be a sponsor here at the conference this year because we use GNU Radio rather extensively across of our locations in New Jersey, Maryland, and New Hampshire, where we're about 450 researchers strong. So I'll say that GNU Radio has been fairly essential to a lot of our signal processing development and prototyping of solutions. And what I'd like to share today is essentially a couple of different programs that are focused on wireless test range explorations. And to do that, I'm actually going to jump on here and just go to the web and point you guys hopefully to the Paraton Labs website. Bear with me. And these, oh, uh-oh, did I type it? I must have typed it wrong, huh? Let's try that again.
Just type in the pound GNU Radio 2022 and then.
Oh yeah, pound GNU 2022. All right, sorry about that. I promise not to go to any shady sites yet. Okay, so two projects I wanted to chat about are about, like I mentioned, wireless test ranges. Number one is how to understand a little bit more about what's going on in the spectrum. So we have a solution called SecureSense right here that is essentially a suite of distributed signal processing sensors that are heterogeneous in nature to help you provide a user better understanding of what's going on in the electromagnetic spectrum. So signal detection, signal classification, even to localization, particularly so that you can utilize spectrum in a much more efficient manner. So this is our dashboard right here, and I'd encourage anybody interested in these types of algorithm developments and deployments. Take a look. If you have questions, reach out to us. We're actively looking for folks who kind of want to jump on and explore implementing these solutions and researching new designs. Here's a picture of some of the sensors that we have. This is one of our bigger ones. We do have some smaller, more man-packable mobile solutions. And again, yeah, please take a chance, take a look through here. We have many of folks from Paraton Labs who would be interested in chatting with you if you're looking for a position in this area. So this is about understanding what's going on in the spectrum, but there's also scenarios where you want to use infrastructure and it's hard to use existing infrastructure because maybe you have a device that's not capable, or you have something like you may be far too mobile. So 4G, 5G standards have certain limits on how fast you can move. Typically, they consider scenarios where you have pedestrian models where people are moving through urban cities, or you are on a train. But if you are on a wireless test range that maybe like Edwards Air Force Base or something like that, it would be fairly advantageous for aircraft to be able to use existing infrastructure for comms, and they can't do that because they're moving too fast. So there are solutions out there. But they are typically not unidirectional, or they're specialized. So we have a product called Velocity, which attempts to address this problem as well. Again, point you to the lab's website right here, where it is a smart informed Doppler precompensation, so that you can essentially run in C-band up to Mach 1, L-band Mach 4, I want to say. And close links with existing commercial infrastructure. So we've demoed this to a degree recently and have pretty high bidirectional data rates whereby you can use that infrastructure. So it's a array of, it's a hardware applique that goes on top of a COTS UE that is, of course, mobile, and a smart software handover solution that gets embedded into the G Node B. So again, we've tested this for 4G and we have some plans coming up for 5G. So just wanted to cite those two types of programs. If any of these things seem of interest, talk to anybody from Paraton Labs around here. If you guys don't mind, I'll raising your hand real quickly so people know, or when you're chatting, you hear somebody's from Paraton Labs. Yeah, by all means, we're looking for lots of people, whether it's RF machine learning, data science, just general SDR, comms development. Yeah, we're looking to hire. Final thing I will say is yesterday's talk, Luke Bogner presented some RFML work. Josh talked about how to properly do some GR debugging, which was very nice. And then I guess Thursday, Dr. Garrett Van Oy is going to be chatting about inference as DSP, and then we have a few workshops in the house. So again, very happy to be here and happy to answer any questions afterwards, but definitely took more than my time. Thanks.
Okay, and we have our final lightning. There you are. Perfect.
So, hi everyone. My name is Andrew, and I represent USDR project that aiming to kind of optimize experience in ESDR, user experience in ESDR. So basically, we have been working with the digital signal processing for the past decade, and throughout that time, we faced a different problem and issue, and some of them have been solved easily, some of none, but eventually, as a community, we made a great progress in the technology, but the convenience in using SDR devices stays behind, especially for the beginners. Let me explain. So before you go with the simple spectrum analyzer, you need to do a bunch of things like install software drivers. Just a software that requires tons of dependencies, specific operation system, let alone of properly configure everything, and make it happen. So, so we decided to create something new, something that doesn't force you to spend like hours and hours to get a simple app running. Since modern browsers, they are like, they're like pretty optimized and so effective. So all the signal processing can be done directly in the browser tab. So basically, it's no special software, no drivers, no version compatibilities, just a web browser that makes everything easy and time-wise. The overall process is a block-like graph where the web schedule takes care of the data distribution and processing. Each individual block can be written in JavaScript or any other languages that compiles into WebAssembly. So you don't need to rewrite your existing C code, so you can reuse it later and integrate into the platform. Moreover, you don't need to build, let's say, FM decoder or signal or spectrum analyzer from the scratch. So the platform has ready-to-use essential blocks and even application available to everyone, like network analyzer or GSM decoder. So with all that being said, working as a community, we can create a huge library of tools that can facilitate each other in achieving their goals, building applications, and finally with those difficulties, installing and finding software behind. Of course, running a real solution in the browser tab is kind of like inappropriate, but you also have an option to offload execution and processing on dedicated server. Dedicated server or private cloud. So, yeah, only live in UI in the browser. There's another common issue that cloud service has been solved. It's a data stream sharing. So basically, Now you can just plug in device SDR to the platform and share your decoded FM signal or even raw IQ to anyone, of course, if you would like to. So basically, it enables global collaboration in decoding and signal processing worldwide. Even it doesn't constrain you to use a web browser. So basically, you can get shared data streams directly in your GNU radio and vice versa. So we provide for that specific plugin in the platform. So basically, everyone can check it out. Eventually, you can combine sources around the world and do the processing processing of the geo-distributed signal in one place. Another important step in developing wireless application and a signal recognition app is to have a collection of IQ streams with the different SRNL level and signal fading. It's crucial not just to have them, but also have an easy access to them. So we add a cloud storage for that purpose. It looks like a file source in GNU Radio. So anyone can add to your collection your samples, IQ samples, and share with the community. So basically, this project is in active development stage so far. So we encourage everyone just go to usdr.pro, sign up for the early access to this platform, and we would appreciate any feedback, guys, that you can share with us and leave us a comment. So thank you so much, and I can talk later with somebody else out there. Thank you.
All right. Okay, so that was the last lightning talk. Exactly on time, perfect. Do you have a question? Yeah, you gotta ask him. No, we don't have we need to go to the breakout rooms. You can sit over. You can just sit down at the table. Perfect. Thank you. Anyway, so this was the last talk for today, but not the end of the the official program. So we're gonna go into breakout rooms now, and they start right now. So I assume that the organizers are already in their rooms. That's why I wanted to move things on. So I'm sorry about that. So we have 3 breakout rooms now. New to GNU Radio and GRCon, so that's for all the new folks. Documentation and visualization. And then after that, starting at 4:20, we have 3 other breakout rooms, FPGAs, GRC, and SIGMF. And these are, sort of more interactive workshops, not